Okay, until now we have seen how the equations of elasticity are written in the polar coordinates, and we had seen how the strain displacement and the equilibrium equations and the Hooke's law, that includes the compatibility equation and all sorts of Navier's equations and compatibility equations and all the other relations which we had earlier studied in the Cartesian system can be written in polar coordinates as well. So in this particular discussion, we'll be focusing on the application part of it. Okay. And as you know, we have approximated, there's a way to approximate a three-dimensional problem into a two-dimensional problem. I mean, via plane strain or plane stress, the two major theories as such. And we'll be using that. So in this work, we'll be only considering two-dimensional approximations, just so that the interpretation of results, etc., is easier. Okay. So we discussed the so-called general solutions in polar coordinates, and then we'll be specializing to cases of contact and fracture mechanics. We don't study the course contact and fracture mechanics, but we'll see how what we have learned directly applies to contact and fracture mechanics. Let's see, the first topic which we would want to learn is the so-called Michell solution. Okay. Now we had seen that the Bi-Harmonic equation in the polar coordinate, so phi is clearly the stress potential function, is given by okay, so the Bi-Harmonic is given like this, and we had seen how this had come. Sorry, there's a square over there. Okay. Let's look now. I mean, the process goes the same. Eventually, the objective is to be able to correctly identify phi, because if we correctly identify phi, then we can find the stress, strain, and whatever we want at any point in this solid. Okay. Obviously, phi has to be in terms of r and theta only now, not in terms of x and y as was the case earlier. Okay. So to be able to find a solution to this problem, assume a separable form. That form is, you must have seen this before, a variable separation form. So f of r and e of I theta. Sorry, e of b theta. We are assuming this form. It's important to note it's an assumption. Now, b is obviously a parameter which you would want to determine. Now, what we do is you substitute this phi into this Bi-Harmonic equation. Okay, let's see what we should get. Or it should actually be done twice. Let's see. Perhaps it's better that you do this. We have done enough of this since we have begun this course, so I think it's your time to do this. What you have to do is you have to look up the derivation of the Bi-Harmonic form and then just substitute phi as this value and partially differentiate it with respect to r, or partially differentiated with terms of theta and squared and so on. So you should be able to do this. I don't think this is required to be done by me. Okay, so this is something which you should verify, and this is the time to actually pause the video and go and derive this. Please don't proceed ahead without being able to successfully derive this form. Okay, and this comes after you substitute this form of phi into the biharmonic equation. Okay, so this is what you eventually get. Okay, so I hope you are able to verify this equation. If not, let me just try to help you over here. Recall what the biharmonic equation in the polar coordinate was. I mean, in the expanded form, it was dou phi was equal to dou by r square plus 1 by r dou by dou r plus 1 by r square by dou theta square, and then dou by dou r square plus 1 by r dou by dou r plus 1 by r square dou by dou theta square. Phi was equal to 0. Now what I do is I take this phi first. Okay, so I'll remove a phi from here and put a phi here, put a phi here, put a phi here. Let's see, what do I get? I get dou by dou r square plus 1 by r plus dou by dou r plus 1 by r square dou by theta square. Okay, and then dou phi by dou r, that should be in twice differentiable, so that should be e to the power of b theta, okay, 2b theta. Okay, and then you can write it as dou 2f by dou r square plus 1 by r dou phi by dou r is again e to the power of b theta dou r plus 1 by r square dou phi by dou theta whole square. So that would make it, first of all, f of r should be out. Oh, I'm sorry, this should just be 1b. Okay, and then you would write b square into e b theta. Please check if I'm wrong or right. Okay, now let's take e to the power of b theta outside and operate each of the terms as they are. So that would make it dou 4f by r4 plus dou by dou r square into 1 by r dou f by dou r plus dou by dou r square 1 by r square f of r b square. Plus, let's take the 1 by r dou by r into dou 2f by dou r square. Okay, let me just use the same symbol. It's not exactly the best symbol to use, but okay, plus 1 by r dou by dou r over now 1 by r dou f by dou. This is dou by dou r
Okay, now do 2f by 2r square. Thankfully these are all plus signs, so hold on. R square d theta square, the last term, that is f of r by r square d square. Okay, this is equal to 0, and this is the curly bracket. Now since EB theta is not equal to 0, the exponential cannot be equal to 0. So that means we can just write the term in the curly brackets as equal to 0. And this implies that 2 4f 2 r4 plus, now we apply the chain rule, 1 by r 2 3f by 2r cube plus 2f by 2r minus of 1 by r square. Okay, let's apply the chain rule once more. B square can be taken out, f of r minus of so this should be minus 6, I'm guessing. Okay, then b square is out, r square 2f by 2r cube 3, so it should be 2. Let's check this once. R square 1 by r is taken out, t3. Okay, this 2f by 2r. B square minus 2 and minus 3, so that should make it, yes, minus 6 plus b square is out and 1 by r square is out and 2f to r square. Okay, so I'm sure of the first step now. Let's look at the second term. That's easy. So 1 by r let me just write b square outside. minus of 2 by r cube. Okay, then this should go to okay. So luckily this is easy. F is only a function of r, so if you differentiate it, you only get a, sorry, this was not f, right? This was phi, I'm guessing. No. Okay, no, that's right. Let's see, if we are wrong, we'll get to know. And this is 0. Okay. This implies that 2f to the power of it 2f. Sorry, let me just check the last term over here. Let's see, so this fr is coming just because we have written it like that. Anyways, f is a function of r only, so not a problem. 2f, so I'll just remove that here. 2f by p square by r cube dou f by 2r minus 2f square by r to the power of 4 2f is equal to 0. This implies okay, so f dash has one term minus 1 by r square minus 1 by r cube plus b square by r cube. Okay, and then let's see what does f has. minus 6b square by r4 minus 2b square by r to the power of 4. Okay, let's see what do we have over here. Whatever calculation mistakes would be there, it should be visible now. Okay, so far so good. So it seems a factor of 2 is missing over here. Let's see. See, so this f double dash, it seems that this 1 minus r square should somewhere be over here. Let's go back and check. B square by r square T2f square, yes. Let me see this term. I'm sure if you have done this yourself, you should have figured out the problem. But let me just see this. Okay. Let's go back. It should be. Hold on. 2 by 2 r square. So we have partially differentiated this term into these two terms, chain rule. So 1 by r, it should be correct, yes. Then dou f by dou r, it seems to be right. Now let's look at the other term, dou f by dou r. So that is minus 6 plus 2 f by dou r square. Okay, that's fine. Di r dou 2 f square. Minus 1 by r square dou f by dou r. I see dou 2f. Good. So let me now just check the first term. Okay. Plus 2 by 2 r square by r 2f by 2 r plus okay. So what I'll do is I'll leave this part for you. Okay. Eventually I have to write that there is some minor error somewhere which you should be able to find. Correct the above and derive f to the power 4 plus 2 by r f to the power of 3, sorry, not to the power but 3 time derivative. Okay, and minus 4b square f dash plus b, sorry, r square plus 1 minus 2b square r cube f dash plus b square 4 plus b square by r to the power 4 f equal to 0. Okay, so you should be able to arrive at this by correcting the error which I couldn't find in a few minutes. I should think it should be easy. Now to be able to solve this equation which is written in purple, you have to do this change of variable which is r e to the power psi. Okay, and once you put this into this, you should be able to get f of 1 2 3 4 minus 4 f 1 2 3 plus 4 plus 2b square f minus 4b square f dash plus b square 4 plus b square f is equal to 0. You please verify this, that after you substitute you should be able to get this. Obviously the prime over here denotes a differentiation with respect to psi, okay, in this equation. So 4 times means okay, something like this. Now you want to solve this equation, and for that the usual method is just put f is equal to e to the power of sort of a psi, okay, and this, if you put it over here, you should be able to get two equations, sorry, two terms, a square plus b square into a square minus 4a plus 4 plus b square is equal to 0. I think this should be easy, right? 4, this is equal to a to the power of 4 ea, okay, and similarly f to the f3 would be a cube ea psi, and so on. So you can substitute each of these terms into this equation, which you should have verified by now. Okay, don't proceed by not verifying it. It may look easy at once, but I think doing that is gives us the real idea. Okay, now the roots of this equation can be a is equal to plus minus ib, okay, or or A, or the same can happen with B. So B is equal to plus minus IA, and B is equal to plus minus I A minus 2. So either of them would be true. Okay, or this and this, or this and this. Okay. So we would want to consider periodic solutions in theta. Okay, and that would mean that B equal to In. This also implies that A will be integer. Okay. Is an integer. Okay, so B is equal to In would mean, because just A equal to plus minus IB, and this would be plus minus I into In, and this would mean plus minus minus N. Okay, that means that A will also be an integer. Okay, so very clearly you would have this repeated roots occurring. Okay, meaning that if B is equal to 2I, then A will be equal to plus minus minus of 2. Okay, and B is equal to 3I, then similarly. So you will have lots of repeated roots in this problem. Okay, now the complete solution of phi over here, remember, don't lose sight of phi was okay, and f had been taken as e to the power of a psi e to the power of b theta. Okay, and clearly there was some variable, a change of variable which we had done. Okay, so if you have phi in terms of r theta, then you will be able to find the stresses at any point, because r theta will be the position of any point in the solid. So the final solution which you will get after being able to solve this is credited to Michell, and that's why it's called a Michell solution. Okay, so it looks like this. I'll have to write the whole form. Let me just write it as log A1. The proof of this is outside the syllabus of this course, outside the scope of this particular course, but in your text you have the reference of it. You are free to check it if you are interested in the entire derivation. Okay. Sorry, it should be A11.
So by looking at the time which I am taking to write this, I hope you have some idea about the time it would take to actually derive something like this. Again, as I have said, derivation is out of scope of this course. I'll just write it here to make it forward. Okay. So this is the general form, and clearly where AN, ANM and BNM are constants to be found. If you can find all these constants, you have the exact value of phi for a given r and theta. And once you have the value of phi at a given r and theta, you can just substitute it, the Airy stress function, into the expressions of stress, sigma r, sigma theta, sigma r theta, and you would have the value of stresses over there. Okay. What we will now be doing, we will obviously not be taking this entire general Michell solution. We will be only taking pieces of it. In the sense, we will be taking only, say, a few terms out of it based on our need, and we'll give a justification why we are taking those terms, and then we will try to find solution and applications to problems eventually leading to contact and fracture mechanics. Okay. One of the things which you should note, that by ignoring a few terms of this, okay, or taking a few terms of this, will make no difference to the equation of equilibrium, in the sense whatever phi you take, okay, out of, say, you have taken term 1 plus term 2, okay, and then you calculate sigma r, sigma r theta, sigma theta theta at a given point, then equilibrium equation will automatically be satisfied even with these terms. Okay, so it is not a problem to be taking only few terms and ignoring the rest of them for reasons which we will discuss. Okay, so nothing changes as far as the solution is concerned for our problem. So let's now see what can be done. Okay, let's see. Okay, let's first take the so-called axis symmetric case. Sorry, axis symmetric case. Okay, field equations over here. What does this mean? Independent of theta. Okay, so say if you have this as your coordinate axis and this point is r comma theta and theta, so whatever value of stress you get over here, theta, okay, that will be independent of theta, meaning at this distance r you can take any theta and you would have the same values of stresses everywhere. Okay, that's the meaning of this axis symmetric case. Okay, let's see how we can proceed. So from this phi which you have, okay, this phi, only take the terms which are independent of theta. Okay, so you cannot take this row now, you cannot take this row now because there's a theta, there's a theta, there's a theta, there's a theta. So ignore all of them and only take the first row, because that's the only terms which are not dependent on theta. Okay, so Phi should be taken in this case. And this choice, by the way, I mean, in what to take and what not to take, looking at the problem, comes by experience. So if you are not able to yourself think just by looking at the problem, what terms should I take from this general Michell solution, it's not a big deal. I mean, it comes by experience over time. Okay, so I will just take the first row. Unfortunately, I'm not able to show that, but okay. So this is log of r plus a2 r square plus a3 r square log r. Okay. Now what we want to do is, we had already seen how the stresses sigma r theta and sigma r theta in two-dimensional situation looks like. So just to remind you, we already had, say, sigma r was equal to 1 by r dou phi by dou r plus 1 by r square dou 2 phi by dou theta square. Sigma theta was dou 2 phi dou r square, and tau r theta was minus of dou by dou r 1 by r dou phi by dou theta. Okay, now if you substitute phi in, so if we substitute phi which we have taken, which is independent of theta, into each of these expressions, we should be able to get sigma r is equal to 2a cube log r plus a1 by r square plus a3 plus a2. Sigma theta would be 2a3 log r minus a1 by r square plus 3a3 plus 2a2. So this is 2a2, and tau r theta is equal to 0. So I will just do the easiest case of them, which is tau r theta is equal to minus dou by dou r into 1 by r. Dou phi by dou theta is equal to 0 because none of the terms which you have in this phi are dependent on theta. So that would make tau r theta 0, and similarly the other two also you can do. Okay. So once you have found the stresses, you can now use the Hooke's law to find strains. Then use strain displacement relations to find displacements. Okay, so you should be able to do this and find what u r and u theta would be looking like. Okay, so do this. Okay, and find out that u r should be equal to 1 by e. For this is for plane stress, by the way, as has been mentioned in your text. Okay, and u theta in this case would be 4r theta e by a cube plus a. Okay, so they will be so-called ABC will be the constants of integration over here. Now I would want you to do this anyways, but let me do a problem over here, which is 7.22. Okay. What this problem does is it integrates the strain displacement relations. So I am assuming that you would be able to do this by, I mean, you have the stresses, now you can use the Hooke's law to find the strain. Once you have the strain, you would want to integrate those relations and find the displacements. So let's see what the strain displacement relations are, and so this is one of the questions from your text. ER is equal to dou U R R. E theta is equal to 1 by R. E theta theta, E theta, whatever you would want to call that. It's a normal stress, so normal strain, and this is the shear strain. Okay, so you should be able to show that the most general form of UR would be A sine theta cos theta, and U theta would be equal to A theta theta plus CR. Okay, let's see how this can be done. Obviously, A, B, C, small a, B, C are the constants. So let's see. If ER is, just assume that for the vanishing strains, I mean, if ER, E theta and ER theta are all equal to 0, then in that case, DUR by dou R implies UR is a function of theta. Similarly, if E theta is also equal to 0, that would mean that 1 by R UR plus dou U theta by dou theta is equal to 0. This implies dou U theta by dou theta is equal to minus UR. Okay, this implies minus of F theta, and this automatically by integration means that this should be equal to minus of F theta d theta dr. Okay, now if ER theta is also equal to 0, then that would mean that obviously 1 by R, see, half cannot be equal to 0, so that would mean is equal to 0. Okay, this would mean that df theta, okay, so UR is equal to F theta from here, so d theta, I'm replacing dou by d because now we know that it's only a function of theta. okay, plus u theta if you differentiate with respect to r, okay, this is u theta by the way, and then you should get f of theta d theta is equal to g of r minus r d of gr dr. Okay, so just substitute u theta from over here and you should be able to. Now for this expression to be true, you must have the left hand side equal to the right hand side equal to constant. See, one of the sides is only in terms of theta, the other side is only in terms of r. The only way both of them can be same is only when it's constant. Okay, so this would mean that df of theta d theta plus f of theta d theta equal to c. Okay, and since this is a constant, this would automatically imply that if you differentiate it, plus f of theta is equal to 0. This implies that f of theta is equal to a sine theta plus b cos theta equal to ur. Okay, so this is the most general form. You have to be able to solve this differential equation. You just take f of theta is equal to a sine theta b cos theta, and you will see that it satisfies this equation. Okay, now once this is done, obviously then there is this other part which is also a constant, this particular part. So we would want to write it as g of r minus r dg of r is equal to c, and d2g. So we have to use the same symbol c. We can't use some other constant because the value is the same constant for this and this. Okay, so that would mean dr square is equal to 0. This implies that g of r is equal to cr plus d, and that means that u theta is equal to a cos theta minus b sine theta plus cr plus d. cr plus d. Okay, so if you now go to er theta, okay, you should be able to get that er theta is equal to minus d by 2r, and because er theta is equal to 0, so you would get d is equal to 0. So you will be able to get that the most general form is a sine cos theta and u theta is equal to a cos theta minus b sine theta plus cr. So do go through this and you should be able to verify this. Okay, pause the video over here and verify that you can get ur and u theta in this form. Don't move ahead without this. Okay, this was for clearly plane stress, as I had mentioned. And for plane strain, how would you go? So there is a transformation table which we had discussed. it was how the constants are related in plane strain and plane stress. Okay, so that must be used to come from one part to the other. So coming from plane stress to plane strain, E has to be converted to E into 1 minus nu square, and nu has to be converted to nu by nu. So once you make these two substitutions in the above equations, you can derive the answer for plane strain as well. So this is how you would always proceed. I mean, there's no need to start from the scratch if you want to convert from one approximation to the other. Now this is the trick. If the body contains the origin, includes the origin, then then stress is then A3 and A1 must be equal to 0 for this is finite. Let's see what and how are we saying this. We had written sigma r is equal, let me just see this over here. So you see this is sigma r comma theta. Now if r comma theta equal to 0 comma 0 lies within the solid, okay, then A3 and A1 has to be equal to 0. Reason being, for r equal to 0, something really bad happens to log r. Okay, at r equal to 0, something really bad happens to 1 by r square. Okay, so to avoid those infinite and singular things from happening, because that would make sigma r and sigma theta as infinite. Okay, so for this situation we want a1 and a3 to be 0 if the origin is included within the body. Okay, if the origin is not included within the body, it's not a problem. Okay, so this was, sorry, a1. So that's the meaning of this. Sorry, where did it go? Yeah, that's the meaning of this statement. If the body includes zeros, then a1 and a3 must be equal to 0. Okay, now the other thing is, note that a3 term in tangential displacement relation, meaning u theta, leads to multi-valued behavior if the domain geometry is such that the origin can be encircled by any contour lying entirely uh, in this. So let's see what that means. Let's see what u theta was. Now come over here, look at u theta. Okay, a3 term, this term is leads to a multi-valued behavior if the domain geometry is such that the origin can be encircled by any contour lying entirely in the body. So theta can clearly take a few values, right? I mean, it's an angle, so it can take any values, and this can actually be much better seen in a problem which we would want to discuss right now, this multi-valued behavior. Let's just see that once. Okay, So this is again a question from the text. It's about a cut and weld problem. So you have something like alpha. Okay. I mean, I have somewhat exaggerated how that cut and weld should be. So what you have over here is a small wedge of angle alpha, which I have shown over here. It is removed from this annular ring. Now the ring is then joined back together. There's a welding to be done at this cut section. Obviously, once you have removed this part and then when you join them using a weld, there will be stresses and strains developed. Okay. Because of the loading the stress field which would generate because of this welding, and it produces a axis symmetric stress field. Okay, but the problem will contain a cyclic tangential displacement condition in which u theta of r comma 2 pi minus u theta r comma 0 is equal to alpha r. Okay, so using this plane strain solutions which we had developed earlier, drop the rigid body motion terms and show that the constant A3 must be given by alpha E by 8 pi. Okay, so let's see how we can approach this. So first of all, without the rigid body terms, mm, without the rigid body terms, u theta would only have this term, okay, because the rest of it there is a rigid body term, okay, and that's why remember in this particular problem we had taken the strains to be equal to 0, okay, to get the rigid body motion terms, because the strains were 0, so the only possibility would have been that the rigid body terms would be there in the displacement. Okay, so that's there, and that's where this term was coming. We had shown that last time, and also this was also rigid body term. Okay, so let's write without the rigid body terms what should be u theta. So u theta, let me use my purple pen. U theta would be equal to 4r theta by E into A3. Okay, and you have this jump condition where u theta of r comma 2 pi minus u theta of r comma 0 is equal to alpha r. Okay, this is the so-called cyclic jump condition, because clearly there is this difference which came in because of the cut which you had made, and this would imply, so what you do is you put 2 pi in this one and put 0 in this one. Okay, so you should get 4r by E theta is what, 2 pi, and that is equal to alpha into r. This implies that and A3 obviously, A3 is equal to alpha E by 8 pi. Clearly r is not equal to 0. Okay, so we are not referring to the origin point over here. So the origin is somewhere over here like this. Okay, so this is there again, as I'm saying, I have exaggerated this cut over here. It's actually a very small cut, but still, so that's why this mismatch term is coming in over there, because ideally this should have been equal to 0 if this was not cut, but it's an alpha r because of this cut which had been made. Okay, Now what one does is we want to write sigma r on the outer part of it and sigma r on the inner part. Okay. We have already done that a few minutes ago. Let's see what we had done. We had found out sigma r, sigma theta, and sigma r theta. Let's see. Yes. So sigma r we had written was equal to, let me just write over here in small, 2a3 log r plus a1 r square plus a3 plus 2a2. Okay. So for r0, which is the, say this is the outer radius ro, this is the inner radius ri or ri. Okay. Ri, we should be able to write this as 2a3 log ro plus a1 by ro square plus a3 2a2 3 log r plus a1 ri square plus a3 plus 2a2. Okay, and first thing, since this origin is not within the solid, so there is no reason for us to take a1 and a3 equal to 0. The origin is over here. Okay, so that's why we haven't ignored a3 and a1 terms. That's the first part. And second part is both the inner and the outer faces are traction free. Okay, what you have to do now, use traction displacement relation. Traction stress relation sigma ij nj equal to ti. Okay, and then find out that this relation, if the traction on the outer and the inner face would be giving you 2a3 log r naught plus a1 r naught square plus a3 plus 2a2 is equal to 0. Okay, 2a3 log ri plus a1 ri square plus a3 plus 2a2 is equal to 0. Okay, so this is something which you must do. You have already seen how this works, and in this case you have to construct the outward normal, and obviously for this plane it will be somewhere like this, for this plane it will be somewhere like this. Okay, so do this correctly and find out, and because it's traction free, these two conditions can be written. Verify this. Now you want to solve for a1 and a2. Okay, you can get it as a1 is equal to 2ri square ro square log of ro by ri alpha e ro square minus ri square by 8 pi minus ro square 16 by r square minus ri square pi. Mhm. So the reason you can do this is A3 is something which you have already found out over here. Okay, so just put this A3 in this. So the only two unknowns will be A1 and A2, and these are two equations of two unknowns. You should be able to get this. Please do this again. Don't just assume that you have done this. And once this is done, I think you have understood this problem of what A1 and A2 and A3 and A4 do to this. Okay. So this is the multi-valued behavior, and that multi-valued behavior is over here, sort of. Mhm. So that was the problem which we had with us. Okay. Now let's come back to our discussion. That even though, remember how we had discussed this section, we had begun discussing this. Okay, by taking only some terms of this Michell solution, saying that just drop the terms which have a theta, because the stresses which we expect in our problem will not actually depend on theta, and hence we took out these 1, 2, 3, 4 terms, because they were the only 4 terms in the general Michell solution which didn't have a theta term. Every other term had a theta. Okay, now it so happens that it's not the only way to find axis symmetric stress field. Okay, I mean, there may be cases in which some of the other terms also, and this is a question which should have occurred to you when I had said this, that just by ignoring the terms here doesn't necessarily mean that the stress, I mean, it's all the terms which will never contribute. I mean, you may still have a theta in phi, but it may just not contribute to the stresses. Okay. So let me take up one. Let me take up this A4 term. Okay, take up this A4 theta term. I'm just taking it as an example, just to prove that what we had done was not exclusive. Okay, not all axis symmetric stress fields come from Airy stress function taken by just taking this phi as what 4 terms was a naught plus a1 log r plus a2 r square plus a3 r square log r. Okay, I am now taking an additional term which is a4 theta. Okay, and I will just see the contribution of stress because of this term. Okay, this can also come with this phi plus a4 theta, no problem, but I'm just separately taking the contribution of this a4 term, because I have already shown that, I mean, it's easy to see that phi, if you don't take if you only take these 1, 2, 3, 4 terms, then you will never have a r theta, sigma r and sigma theta. So in this case, if you now go back to your expression, let me just see, where did it go? Okay, let's see how I can okay, can I copy? Let me just put that over here, paste. Okay, that's good enough, I think. Okay, now if you look at sigma r due to this term, you will have the first term is 0. The second term will also be 0 because theta is only 1 and you need a 2-time derivative. Sigma theta would be equal to 0 and tau r theta, okay, that would be equal to a4 by r square. Okay. Okay, so this tells us that this is also axis symmetric. Okay, because all the stress fields which you see over here are independent of theta. Okay, and this could be used to solve problems with shear fields that produce tangential displacements that are independent of theta. So let's see if we can take up some case. Okay, let's see how the tangential equation show up. So this is again a question from our text. It is to develop the general solution for the axis symmetric case. So you want to show that I think these are parts of the question which you were supposed to do anyways. We have done it in several parts. Okay, then this would be 1 minus nu a3 r log r minus 1 plus nu a3 r plus 2a2 1 minus nu r plus a sine theta plus b cos theta. U theta is equal to 4 r theta by e a3 plus a cos theta plus b sine theta plus cr for the axis symmetric case. Axis symmetric case. Okay, so in this one you already have this sigma r is equal to 2a3 log r plus a1 r square plus a3 plus 2a2. We had seen how we had got this. And okay, now let's just take up the displacement or relation dou u by dou r, and this is related to the Hooke's law for the polar case is this would imply, sorry, this is dr ur is equal to, you have to perform an integration over here. So what you do is you just put sigma, let me just write this as again, dou ur by dou r is equal to 1 by e, put sigma r which is 2a3 log r plus a1 by r square plus a3 plus 2a2 minus of nu 2a3 log r plus 2 sorry plus nu a1 r square should be a minus 2 nu a2. Okay, fine. This means that you should have a 1 by e, and then you should have
sorry, theta. Okay, minus plus minus minus. Okay, so log 2a3 minus 2a3, sorry, 1 minus nu log r plus a1 1 plus nu by 1 by r square plus a3. There's one more actually, a3, and that's a very innocent looking a3. That would be 1 minus 3 nu. Okay, and okay, and then you have, let's say, a2, that's 2 minus, so 1 minus nu. Okay, so you just integrate this over this r, and you will have a constant of indefinite integration. So you write it as 1 plus nu by r minus a1. Okay, and plus 2 into 1 minus nu a3 r log 3 minus 1 plus nu by 3 r plus 1 minus nu r plus f of theta as a constant of integration. Similarly, you please put this 1 e theta is equal to 1 by r u r plus u theta, and you would find that this is equal to, using the Hooke's law, as sigma theta minus nu sigma r. Sigma r. Okay, substitute sigma theta, sigma r theta, and you should be able to write something about u theta. So that would be dou u theta by dou theta is equal to 4 r a 3 by e minus f of theta. Then similarly you would have r theta, e r theta, and this would be equal to 0 because of the Hooke's law. Okay, see how e r theta looks like, because tau r theta is 0, I'm assuming. Yeah, tau r theta is equal to 0, so because of the Hooke's law this would also be equal to 0, and then you put all of that together, including the rigid body motion terms obviously, which you have to take. Then you should be able to arrive at this. Okay, now this has happened because you have started with 1, 2, 3, 4 terms from phi, and then you have got this. If you really wanted a term in which u theta is independent of theta, then you could have included the fourth term, which was a4 theta. Okay, because that term would have given you something like this, which wouldn't have given you a theta. So this is an example how one case was taken over here. Okay, so just see that, and perhaps you should be able to do this case. See, by now repeat this exercise by taking 4 terms. Okay, I'll write this over here. Repeat this by taking phi is equal to 1, 2, 3, 4 terms which you have taken just now.
plus taking this a4 theta, okay, and see what ur and u theta you get. So that's the difference it makes to take or exclude a term from phi. Okay, so it will change the entire way you look at a problem. Now, since you are referring to this so-called multiply connected regions, remember theta can, we have seen an example of why it's a multiply connected region. The compatibility equation in this case is not sufficient to guarantee single valued functions. Okay, so let me make that code. For multiply connected regions, the compatibility equations are not sufficient to guarantee single valued displacements. Okay, what we do now is we can find the sort of look at the displacements directly from the Navier's equation. Okay, so the Navier's equation was coming when the equilibrium equation was written in terms of the displacement. Okay, we don't look at the compatibility equations where the stresses were written in terms of the compatibility equation, because compatibility equation in cases like this, which are multiply connected, does not make any sense. Okay, and we have seen that cut and weld example. Think of why that is a multiply connected domain. Okay, so you don't invoke the compatibility equations now. For the axis symmetric case, you please invoke the Navier's equation, which you should have seen before. U as a displacement is only dependent on there's no E theta term. So the Navier's equation would look like just hold on. Okay. Okay, so this should look like dou ur by dou r minus 1 by r square u equal to 0. Okay, and just by looking at it, you can say, I mean, this is a simple equation. Since ur will only depend on, I mean, this actually dou is not even needed. You should only have a d. Okay, because there is no other dependence. Du by dr. So looking at this ordinary differential equation, you can just say that the solution like this will satisfy. C1 and C2 are constants. Now this solution, if you look, is not looking like, let's see, ur over here is not really looking like the you are over here. Yeah, you are over here is not really looking like you are over here. Okay, remember that you are, which we have just got, is actually looking like C2 1 by R. Okay, and it's not like the one which you have in front of us. Okay, now why did this happen exactly? That's something which you have should be should be able to answer. Why is it not looking like this? I mean, what did we do different this time? Okay, the reason you did this because when you were trying to find this, you assumed u theta was equal to 0. Remember, this was taken as u r e r plus u, sorry, e theta. Okay, and you had assumed this when you had found this. In this case, on the other hand, you made no such assumption. Now, if you take this ur, okay, and then try to write the stress terms, okay, I mean, you take this and write the, actually, you should write the stress terms, write sigma r, sigma theta, tau r theta. What will you find? You will find that there is no log term. Okay, log term was there in the single valued assumption, but here since we were considering multi-valued and we had axis symmetric forceful condition of u theta equal to 0, you will not get a log term. And what is the implication of a log term? Now the origin can be within the solid and A3 need not be 0. Okay, because that is what was required over here. Look at this one. Okay, we had said that the origin r will be equal to 0, then this will blow up, so we don't want it to blow up, and hence we said that a3 and a1 forcefully were 0. But now if log r is not even coming, I don't know how you should be able to see this problem, but you don't have to forcefully take out constants. So please do these things. I mean, these are not left for us to just look at. You should write down the term and then be able to make these discussions. So please verify it. Do not proceed ahead before doing this. This is the only thing which will help you interpret the results over here. Okay, so one of the other cases which must be discussed over here is the so-called thick-walled cylinder. Thick-walled cylinder, pressure vessel design. Okay, very the same idea. In principle, this situation looks like this. There's a thick wall, and then there is a pressure P1 inside. Obviously, it will be around like this, and then there is a pressure P2 which is outside. The inner radius is R1, the outer radius is R2, and you are supposed to find the stress at any given point like this. Okay, now this situation is very common for us. Think of this: if you were in a submarine which was buried deep into the ocean, then P1 has to be 1 atmosphere, because people like humans have to survive in this P1 inside this pressure vessel, and P2 will be depending on how deep you are into the ocean. Okay, so and it's a lot, right? P2 will be much greater than P atmospheres for this case. Consider a case now in which you are in an airplane which is flying, say 5, 6, 7 kilometers above the earth, and perhaps more depending on where how they fly. Normally, the international flights fly much higher than the domestic ones. Anyways, in that case itself, P1 has to be 1 atmosphere because we have to live. However, P2 will be less than, okay, because the atmosphere keeps on becoming rare as you go up, and eventually, if I mean, if we have this manned mission going to the moon and all, then there'll practically be no atmosphere. So P2 will be 0 in that case, but P1 still has to be maintained at 1 atmosphere for humans to live, or around that value. And similarly, you can have the LPG cylinders which are there used in cooking in most of our homes. P1 will have some value, uh, higher value clearly, and P2 has to be atmospheric pressure. Okay, so because it's kept in the kitchen where the outside pressure is P2, so P1 will be a higher value than P2 and so on. So there are lots of applications. I mean, all the petroleum products, diesel and petrol containers which you see on the highways going to the petrol pumps and all, they also have this. The outside pressure is atmosphere, and inside there is a pressure which keeps the hydrocarbons at the levels you would want them to be. Okay, so this is a very, very, very important problem from our everyday perspective, and the eventual idea is that the cylinder should not fail in all the applications. And how would we know whether it fails or not? Well, you have to calculate sigma ij at this point, and then using the sigma ij, you have to use one of the failure criteria to check whether it is permissible or not. And if it does, then it means that it is safe at this point. If it doesn't, it shows that it will yield at this point. And hence you can use that in designing such cylinders. Okay, so we will use sigma r equal to a by r square plus b, and sigma theta is equal to a by, sorry, minus of a by, this is clearly an axis symmetric case. Sorry, should, okay, so this is the minus a by, see, we are ignoring the log terms to start with. So see if it's written somewhere near. Okay, so we are taking A3 equal to 0 in the previous case, and then you would get A1 by r square plus 2A2 for sigma 3 sigma r, and sigma theta would be minus of A1 by r square plus 2A2. So 2A2 has been written as B in our case, and this is how we have got. So let's see, and I'll ask you some questions. This is what we have got after ignoring the log terms. Okay. Now, what are the boundary conditions? Again, I mean, the traction boundary conditions is what you would be using, and don't write the stresses directly. I am writing the final answer. You should always equate traction, not the stress. Okay. I am writing this as verify. Okay. Now, once this is done, you would want to just put R1 into this and R2 into this and find out the values of A and B. Okay, so that should give us A is equal to R1 square, R2 square, and okay. So using these two conditions, we don't know anything else since we'll be using these two conditions, and two conditions are enough for A and B, two unknowns, and B would be equal to R1 square P1 square minus R2 square P2 square by R2 square minus R1 square. Okay, now we would want to put this A and B back to these expressions to find sigma r and sigma theta. So I'll just write out those expressions. You should also substitute that. Please don't just walk with me. This is steps. At this stage in this, you should be very well doing. Okay. So this is sigma r and sigma theta, which we would get for clearly any value of r between r1 and r2. Okay. Now this is what you would get for the case which we have just discussed. And if there's a plane strain assumption, okay, then you would have to find the plane strain. You would get sigma z is equal to nu. Then because we have found sigma r and sigma theta, so this should not be a problem. Sorry, this. Okay, so this should be nu sigma r minus sigma theta, that is equal to 2 nu r p1 minus r2 square p2 square minus r1 square. Okay, now since you have found out the stresses at a point, you use the Hooke's law. Okay, and then do the displacement again, integrate the strain displacement relations. You would find that we get something like this. Feel free to use the earlier relations which you have derived, but not ignore doing these derivations. Okay, either way, you either do it from the scratch or see if you can substitute what we have done before, but don't ignore doing them. I can't emphasize it enough. Okay, so one of the things which you really should love about the stress field over here, that it does not depend on E and nu. Okay, it just doesn't depend on E and nu. For this problem with no body force, the stress field does not depend on the elastic constants. But look at the displacements. They clearly do. The resulting displacements do depend on both E and nu. Okay. So this is something which is really important for you to note, that the stress which you find out will not depend on the material as such. It will only depend on the pressure and the radius R1 and R2, the inner and the outer radius. But just make sure that the conditions are exactly the same as this one. Don't like learn this. Okay, there are certain conditions which we had taken for this to be true. Okay, now let's analyze this results, or let's say should show it over here. Let's first look at sigma r and r by r2, so it's normalized. Again, this sigma r is also normalized by this pressure P. Okay, so what is P? P2 is taken as 0, P1 is taken as P. Okay, so it is like a situation in which a spaceship is between two planets, between Earth and Mars or something like that. So there's no atmosphere anywhere. Okay, so P1 is equal to P, and what would be sigma R in this case? And R1 by R2 is taken as 0.5 just to be able to plot this result. In this case, the sigma R will go up from -1 to this value of 0. Okay, and sigma theta will sigma theta by P will somewhere go like this. So you should be able to plot both of them and see this result. So the more you go into the distance, sigma r keeps on increasing and sigma theta keeps on decreasing. Okay, so the radial stress decays from minus P to 0. Okay, it increases in the sense from negative to 0, while the Hooke stress, sigma theta is also called the Hooke stress. Do remember this. I found it very embarrassing when I was quite young and I didn't know. It seems everyone around me knew, but I didn't know. Anyway, sigma theta is called the Hooke stress. And this is always positive. It will come out as this graph, and you can always have a maxima found out. So that would happen at the inner radius. Okay. So when the cylinder is thin, okay, you can show that, and there's a reference of the appendix in your text for a thin cylinder. Where did we go? Where did we here? Okay, for a thin walled cylinder, the thickness will be very less. So you can write sigma theta is equal to P R naught by T, and T is equal to R2 minus R1. R naught is equal to R1 plus R2 by 2. So this is the Hooke stress which you would get for a thin walled cylinder. You can first of all derive this and then learn this. It's an important result to learn. Okay, and then you can use problems, the solutions which you have just developed for certain other situations, like if you have a pressurized hole in an infinite medium. Okay, you should be so if you have a situation like this, it's an infinite medium, and then you have this pressure P inside, radius is R1, R2 is infinite. Okay, so P2 will be equal to 0, R2 will tend to infinity. Okay, and R1 and P1 is finite. If you take these limits, okay, into these expressions over here, okay, you should be able to find out what the solutions would look like. So let's see if we can take one case. Let me just write out, because I think rest of the things you do it anyways. Let me take one. So you are, let me use a, the sigma r is equal to r1 square r2 square by p2 minus p1 by what r2 square minus r1 square 1 by r square plus r1 square p1 minus r2 square p2 by r2 square minus r1 square. Okay, now divide both sides by, I don't know, r2 square. Is it a good idea? So this r2 square clearly gets cancelled. So let me just, okay, let's first put p2 is equal to 0. Okay, that would make this as r1 square r2 square minus p1 square minus r1 square 1 by r square plus r1 square p1 by r2 square minus r1 square. So let's take it as r1 square minus p1 by 1 minus r1 by r2 whole square 1 by r square plus p1 by, so nothing can happen actually over here. Okay, now if you do apply the limit of r2 tending to infinity, you should get this as minus of p1 r1 square by r square, and the other term should be equal to 0. So that is what would be sigma r, and similarly you can find sigma theta and sigma z. So I'll just write, for a case like this, we would get sigma r is equal to minus of p1 r1 square by r square. Sigma theta is equal to p1 r1 square by r square, and sigma z is equal to 0. And then you can look up the displacement field like this. Okay, and just make the same substitutions over here to get uz is equal to 1 plus nu by e p1 r1 square by r. Okay. Okay, so in this particular case, you can clear, oh sorry, this is what's P1. In this case, you can see that the stress and displacement field decrease to zero as r tends to infinity. So as r tends to infinity, sigma r tends to zero, and ur also tends to 0. ur also tends to 0, but the rate at which it decays, okay, in the sense dou sigma r by dou r and dou ur by dou r, they are different. So this decays to the order of 1 by r square, as you see, and this decays to the order of 1 by r. Okay, you can see the terms over there, and so this is a faster decay. Faster decay, higher rate, whatever you would want to call it. Okay, and the implication of this is that the stresses are proportional to the gradient of the displacement. Now if you take a gradient of this displacement, okay, then you would clearly have 1 by r square term, and that would be related to the strain, and then the same strain, because of the linear relationship of the Hooke's law, will be over. So this 1 by r square, which is the gradient of the displacement, will carry over to strain, and this will carry over to stress. So this is something which you could have expected beforehand, and there are some other cases which one can take up, which we'll be discussing now. Okay, thank you. Okay, so after having discussed this situation of pressurized hole in an infinite medium, let's take up a couple of other sort of related cases. The first one being sort of a stress-free hole in an infinite medium under biaxial loading. So you have this infinite medium, there's a hole, okay, no internal pressure, and it is under this remote biaxial loading in two directions. Okay, so let's see what the stress field would look like in a situation over here. Okay, so just like the previous case, in this case also R2 would be tending to infinity. Okay, P2 would be equal to minus T, and P1 is equal to 0. Okay, the if you want to see what the far field stresses would be, in the sense far away from the hole, they would be far field stresses. They would be sigma x is equal to T and sigma y is equal to T. So what happens much away from the hole, the effect of the hole is almost 0. Okay, so you will not find any decay of the stress which is high near the periphery of the hole. Okay, and this is the same as, say, sigma r equal to sigma theta equal to T. So the same can be said for this particular problem. Now if you use the stress results which we have over here, where did it go? This one. Let me just remove this. If you just remove or assume the stress field over here and use this R2 tending to 0, Pt is equal to minus T, P1 is equal to 0, we will get a value of sigma R and sigma theta. Okay, so please verify that you get sigma R as equal to T into 1 minus R1 whole square by R2 whole square, and sigma theta is equal to T 1 plus R1 square by R square. This is something you should verify in this case. So clearly, I mean, in this case, where does the maximum sigma theta occurs? Well, sigma theta will be maximum at R equal to R1, which is at the periphery or the boundary of the hole. Okay, and this value you can write as sigma theta of R1. This is equal to 2t. Okay, so we say that the stress concentration factor, you should have heard about these terms, which is sigma max by T. Okay, this is equal to 2 in this case. Okay, so somewhat being inspired by what we have just done, let's take up another modification in which you will have an infinite medium with a stress free hole under uniform farm field tension loading. So in this case, say if you have an infinitely large solid, there's a hole of radius A. Okay, there's a hole of radius A, and unlike the last time, we only have a uniaxial tension this time. What would be the stress field at any given point inside this solid? Okay, so let's first write the boundary conditions. So sigma R A theta equal to tau R theta A theta equal to 0. I am writing it directly. You should, as you remember, should not write the stress. You should write the boundary conditions of the tractions. Okay, and then it will turn out to be like this. So please don't directly attempt to write stresses like this. I am just writing the final answer which you should do. Okay, now sigma R, so this was obviously at the periphery of the hole. Then at the boundary of this solid, you can write it as T by 2 1 plus cos 2 theta, and sigma theta of infinity comma theta is equal to T by 2 1 minus cos 2 theta. Okay, and let's see, sigma tau r theta, we want to write the shear stress. Let's see what that would be. Tau r theta infinity theta, that's equal to t by 2 sine 2 theta. So of course this part should be very clear. It has to come from the traction displacement relation. This part, okay, how has this come? You have basically a system which is the boundaries are aligned in the x and y direction. Of course, they are infinite, but they are aligned in the Cartesian system. But you have to write stresses in the polar coordinate system. So you have to undertake a transformation. Okay, so let's take a question over here from the text. Show that the general two-dimensional stress transformation in polar coordinate system in terms of Cartesian so we want to write that this must be equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. Similarly, sigma theta should be equal to sigma x plus sigma y by 2 plus minus tau xy sine 2 theta, and then tau r theta is equal to sigma y minus sigma x by 2 sine 2 theta plus tau xy cos 2 theta. Okay, we want to prove this, and once you have this, all you can do is just directly substitute the terms over here, and then you should have your answer. Okay, so if you rotate the xy system to x dash y dash system by angle theta, then x dash will become r and y dash will become theta. Okay, so say x y, and at any given you have r theta. Okay, so all you have to do is make this rotation, then x dash will become r and y dash will become theta. So you just apply the transformation where the dashed term would be cos theta sin theta minus sin theta cos theta. We have already seen this rotation. Cos theta sin theta minus sin theta and cos theta. If you solve this, you should be able to directly get this answer. Okay, where this sigma ij dash, I mean sigma 1 1 dash would be equal to sigma r, sigma 2 2 dash would be equal to sigma theta, and sigma 1 2 dash or sigma 2 1 dash would be equal to tau r theta. So please do this transformation and find this, because only after this you will be able to write these boundary conditions. Yes, you have to apply the boundary conditions even after this, but you should be able to write this down. Okay, so please verify this. Okay, now let's first consider a case. Assume there is no hole. Okay, so what would be the state of stress if there is no hole? Well, should be quite simple. That should be, let's just put, these are all infinite boundaries. We have the traction T. You would have sigma x is equal to T, sigma y would be equal to 0, and tau xy would be equal to 0. Okay, and this state of stress for a solid with no hole, you could have easily derived using this stress function. Remember to use the coordinate Cartesian system for this one when you write this. Okay, so this has happened by trial. What you have to do, you have to look at the airy stress function for the Cartesian system. What would that be? It would be sigma x is equal to dou 2 phi by dou y square. Sigma y would be equal to dou 2 phi by dou x square. Okay, body forces I'm not taking. Okay, so this will be satisfied if you take phi as equal to ty square. Okay, so this has happened by trial and then you have taken this guess. There was no other trick about it. Now you want to write this phi in the Cartesian polar system. So just take a t by 2 first. Y can be written as r sine theta, x can be written as r cos theta, so this will become r square sine square theta, and this can be written as t by 4 r square 1 minus cos 2 theta. Okay, so cos 2 theta equal to 1 minus 2 sine square theta. That property has been used. Okay, so what does the presence of hole does? It actually disturbs this uniform stress field. Now the stress field is uniform, and a stress field because of the hole, you have seen the previous case as well, it distorts this stress field. But the good part is, I mean, if you are much away from the hole, the stress is exactly the same as it would have been if there was no hole. Okay, just because there is this decaying effect which we have seen in the earlier examples. Okay, now with this, we choose a trial solution with all this knowledge. That includes obviously the axis symmetric terms. Okay, because our answer is not supposed to, I mean, with the whole, it's not supposed to depend on the angle theta. And cos 2 theta terms. Okay, this you have to choose, remember, from that big Michell solution. You have to choose a term that includes axis symmetric term and cos 2 theta term. Okay, the reason we do it, because this term appears as the so-called far field in the far field results. Okay, so that's why we would require to have terms of this form. So let's now go to the Michell solution, the general Michell solution. Here it is. Okay, so obviously we want to choose the far field term. So 1, 2, 3, 4, no questions about that. Then we would require the cos 2 theta terms. Okay, so what would be the cos 2 theta terms? Cos 2 theta terms would come over here when n is equal to 2. Okay, so basically you should have a21 r square plus a22 r4 plus a23 r to the power of minus 2 plus a24 r to the power of 0 into cos 2 theta. Of course, there is cos 3 theta, 4 theta, etc. as well, but we are not taking that. So we are taking only these 4 terms at the top plus these terms in green, because we want a phi which has contributions of the cos 2 theta terms. So let's now go back. Okay, let's see. Yes. Okay, so we'll take up phi, which is again a naught plus a1 log r plus a2 r square plus a3 r square log r. Okay, now the cos 2 theta terms, a21 r square plus a22 r to the power of 4 plus a23 r to the power of minus 2 plus a24 cos 2 theta. Okay, okay, now with this phi, the phi which you have chosen, based on your wisdom that other than this axis symmetric terms, we also require terms which have a cos 2 theta in them. Okay, you would want to have the stresses sigma r. This you can just substitute by putting in the values of phi. Okay, and this should be given as a3. I'm writing the expression, it's your job to verify them. Okay, sigma theta is equal to a3 You see how these cos theta terms will come out so nicely, okay, and they have to, because you must verify these expressions which I am writing after substituting this phi. They have to, because away from the hole the stresses have to satisfy these boundary conditions. Okay, that's the reason we are doing this. So this example is also sort of giving you that experience or wisdom how to choose the terms from the general Michell solution. Okay, so once this is done, now if you look at the expressions, okay, sigma x is equal to t, sigma y is equal to 0, tau x y is equal to 0. Okay, now look at the expressions which you have got over here. There is a log r term. This is not a very nice term to have. Uh, okay, actually, no, because it's not a problem over here, because the origin is actually not I mean the hole is like this, so the origin is not actually lying within the body, so this isn't really a problem. However, it's said that a3 equal to a22 must be equal to 0. Why is this there? For finite stresses at infinity. Okay. The boundaries of this solid should have finite stresses. Okay. So if you want to have that, you must have A3 equal to 0 and A22 equal to 0. Okay. So which are the terms? Let's see. This is the term. Okay. Because when R will tend to infinity, this particular term will become infinite. That's not what we want. Okay, same happens over here. Okay, now the other term is a3. Let's see why that should be there. If yes, I think log r in this case, if r tends to infinity, log r will also go to infinity. Okay, and hence 1 plus 2 log r or 3 plus 2 log r will also go to infinity, and that's the reason a3 and a22 has to be equal to 0, so that at r tending to infinity you have finite stresses. Okay, now let's go back to this boundary condition over here. Okay, we want to, let's see, write this. Copy. So let me just make it small. Okay, so once this is taken, you want to apply these boundary conditions over these stress fields. Okay, so I'll write those boundary conditions. Okay, why is this coming? Okay, so that should make this as 2a2 plus a1 by a square is equal to 0. 2a21 plus 6 a23 a4 plus 4a24 a square is equal to 0. Then we have 2a21 minus 6a23 by a4 minus 2a24 by a square is equal to 0. a21 is equal to okay. So let me just see one of them. Okay, so let's put sigma r a theta is equal to 0. So I'll be looking at this one. Sigma r a of theta, that would mean a3 is anyway 0, so that would make it 2a2 plus a1 by a square minus 2a21 plus 6a23 r4 plus 4a24 by r square cos 2 theta. Okay, and this is equal to 0. Okay, now this I think is the first one. Can you think of a reason why this entire term should be equal to 0? The logic is that it should be 0 for any value of theta, and hence we have conveniently taken theta is equal to what, pi by 4. Okay, for this it should also hold, and hence cos 2 theta will be equal to 0. So theta is taken as pi by 4 over here, and it should work. So this is how you got the first boundary condition. Similarly, your job is to verify the others. Okay, please don't be lazy. Please do this. Okay. Now this system can easily be solved. You have what, a1, a2, a25, a24 and so on. So this should give you a1 is equal to minus a square t by 2, a2 is equal to t by 4, a21 is equal to minus t by 4, a23 is equal to minus a4 by t4, a24 is equal to okay. Now these values should be substituted back to here. Okay, so take these values and substitute it back over here. Okay, once you do that, you should be able to get sigma r is equal to t by 2 1 minus a square by r square plus t by 2 1 plus 3a to the power of 4 3 to the power of 4 minus 4a square by r square cos 2 theta. Okay. And then you would have a sigma theta is equal to t by 2 1 plus a square by r square minus of t by 2 1 plus 3a to the power of 4 r to the power of 4 cos 2 theta. Tau r theta is equal to minus t by 2 1 minus 3a to the power of 4 r to the power of 4 plus 2a
square by r square sine 2 theta. Okay, so this is again something which you should verify. Please don't proceed ahead without checking this. And needless to say, you can once you have found the stress, you can use the Hooke's law to find strain. Once you have found the strain, you can use the strain displacement relationship to find the displacements. So this entire problem as such is solved. Okay, because the only unknowns are displacements and strains and stresses at a point, and you have found them. Okay, now and true to its spirit, you can see there is no term for E or nu in sigma r, sigma theta, and tau r theta. It only depends on the loading, the boundary uniaxial loading, and the dimensions of the hole. Okay, so this is something which works well. Now the hoop stress around the boundary of the hole, so sigma theta, okay, sigma theta a comma theta is given by, just put r is equal to a, and that should give you t by 2 1 plus 3 minus 4 cos 2 theta. I'm sorry, 1 plus, I'm sorry, I was looking at the, so this should be minus t by, sorry, t by 2 1 plus 1 minus t by 2 1 plus 3 cos 2 theta. Okay, so this gives me t into 1 minus 2 cos 2 theta. Okay, and a graph of this is slightly hard. Okay, you have to draw this in terms of theta only. So let me just show it to you, or attempt to show how it looks like. You have to draw this on a theta axis. So let's see, this is as good as it can get, I guess. Okay, not the best drawing, but I would just want to show you the form of it. How this looks like is you have 0 over here, you have 90 degrees over here clearly, then you have 180 degree over here, and obviously this is 270 degrees, and then rest in between is something which you know. Now this particular curve is the so-called sigma theta of a comma theta by t. Okay, so this graph divided by t, so normalized against t, so you would have a 1 minus cos 2 theta graph. Okay, and similarly this particular thing is a minus of sigma theta a theta by t. Okay, and this angle which you see over here is 30 degrees, and this value is 0 at 30 degrees, and coincidentally 210 degrees and 150 degrees and so what. And that's something which you can easily see over here. This value at 30 degree would be what, cos of 60 degree, which is half, and hence sigma theta would become a 0. Okay, and the maximum value of it would be when it's 90 degree. Okay, you can also see that by the graph which is there. So it takes the longest value at 90 degree. So sigma max would be equal to t, sorry, sigma theta of a plus minus 90 degree.
okay, or it is equal to 3t. Okay, so the stress concentration factor for this problem is 3. Remember, in the biaxial remote loading it was 2, in a uniaxial loading it is 3. And this tells us something somewhat important in your practical life. An additional vertical loading to this okay actually reduces the stress concentration. So one of the other things which we had earlier claimed that, well, that stress, the hole only sort of disturbs the stress field and the effect of it gets diminished as you move away from the hole. That's something which you can also see if you try to plot sigma theta by t as a function of r by a normalized. Of course, it would go to obviously 3 over here, okay, and then this is 1, okay. So the stress concentration factor is 3, so it has to go over here, and this is sigma theta of r by a pi by 2 t. So somewhere around 5 with, I guess, when r is greater than 5a, then as if there was no hole. I haven't drawn it quite well, but the actual graph behaves in this form. Something like this, okay. Not exactly 0, but after a while it will be somewhat like that, okay. So at a distance which is greater than 5 times the diameter of the hole, you should have a stress field which is independent, as if there was no crack, no hole, sorry, to distort the stress field. Okay, so this is again a variation in the Hooke stress with the radial distance from the hole. Now, one of the last sort of variations in this case is the biaxial and shear loading cases. So similarly, and then other case looks something like this. We have a hole. So you have first of all take up a biaxial loading, which is the figure on your left. Okay. Now there is tension in the horizontal direction, you can see that, and compression in the vertical direction. So this is equivalent to a pure shear loading on planes rotated 45 degree as shown in B. So if you rotate this, okay, you will be 45-degree rotation, you get something like this. Okay, now solving this biaxial problem is very easy. You have practically done this. Okay, now how would you go about it? Remember, we had learned about the principle of superposition. Okay, so to the problem which you have dealt with, in the sense this one just now, right? You have dealt with this one. You add this problem. Sorry. Okay, and then this would combinedly give you, okay, by the principle of superposition. That's the scientific reason why you can do it in this particular way. Okay, so this is done by adding to the original state another stress field with loading replaced by minus t, this one, and having coordinate system rotated by 90 degree. Okay, so it's this is essentially this being rotated by 90 degree and t being taken as minus t. Okay, now this is something which you should do. Please do this. Okay, and verify that you get sigma r Just like the earlier cases, the sigma theta max would be found out. equal to sigma theta A of pi is equal to minus 4t, and sigma theta A comma pi by 2 is equal to sigma theta A comma 3 pi by 2 is equal to 4t. So the stress concentration factor in this case is equal to 4. It just keeps on going up, doesn't it? Okay. So in summary, the equal biaxial tension in the boundary gives a concentration of 2, stress concentration factor of 2. A uniaxial far field loading gives a stress concentration factor of 3. Okay, and equal but opposite biaxial loadings, okay, which is there in this problem, gives the stress concentration factor as 4. So when it comes to severity, it seems this is greater than this. Okay, and is greater than this. So this was a SCF of 2, this was 3, this was 4. So this seems to be the most dangerous because this will concentrate the stress at the periphery of the hole the most, and hence it's at the most risk of failing for the same values of T. Okay, so this is something which you should keep in mind. Perhaps in next time you have to practically use this idea. Okay, how should we pull or push something which already has a hole inside it? Uh, this is something perhaps you can use. Okay, just like a side note, if you have a problem in which you have a hole, and whether it's pressurized, not pressurized, doesn't really matter, but the boundaries of the solid are not at infinity, in the sense the hole is not so small that the boundary can be assumed at infinity, then also the same problem can be done, but it is slightly more complicated. Okay, so this is the thing. I mean, if you want to solve this problem, okay, where this hole, if the hole, so even in this dimension, if the hole is small compared to the boundaries, perhaps you can use this case. But if the hole is also of a dimension in which it cannot be actually ignored, then how do you solve this problem? We don't have to discuss this, it's outside the scope of this course. Okay, but what you should know, that you have already seen that the decay because of the presence of the hole is usually off after some distance. In this case it was greater than 5a, so you can take a shot at seeing whether it is enough to approximate the method which you have just developed or not. In the sense, how small should the hole be can be seen in terms of how it decays, the stresses decay from the hole. Okay, so this is something which you can check, and if it works, good enough. If not, there are various other numerical methods which you can take advantage, because it somewhat becomes quite cumbersome trying to look at the analytical solution, okay, towards this. Okay, so we'll be taking up the wedge domain problem now, and let's see what it is, and then we'll be able to do lots of interesting things with this wedge domain. So if you have your x-axis like this, y-axis like this, and then so this is your wedge, this angle is beta, this angle is alpha. If there's any point of interest, something like this, let me show it in a different color. So this is r comma theta, meaning this angle is theta. Okay, and the distance is obviously r. So the eventual objective is again to be able to find the stress, strains and displacement at the given point r theta within this wedge domain. Okay, so that's how this is. So the two boundaries of this wedge is defined by theta is equal to alpha and theta is equal to beta. Okay, and we will see how this can be used to solve problems of contact and fracture applications, mechanics. Okay, so again, I mean, you start off with the Michell solution which we had written, the general Michell solution. Okay, the very big one somewhere. Let's see, where did it go? Should be at the start. So yeah, somewhere over here, yeah, this one. So from this general Michell solution, okay, I'll just rub out these parts now. Theta. You want to have, you want to take out terms which will be useful for your particular problem. Okay. So what is the criteria for choosing over here? The criteria is that you have to take out the terms that are bounded at the origin, okay, and they give a uniform stress on the boundary, because the boundaries of this wedge are having a uniform traction. So you want to take out the terms which eventually give you uniform stresses on the boundaries, and it should not be unbounded at the origin. So clearly you will not be seeing log of r terms in this. Okay, that's the first criteria. So let's see. To take out, you will take out the terms which look like this. Let me now just come back. And most of it comes by experience. So I mean, just by looking at the problem, if you are not able to decide what terms to take out, it's fine. I mean, gradually you will be able to learn how the thought process behind selecting this. So we take out this r square a2 plus a6 theta plus a21 cos 2 theta plus b21 sine 2 theta. Okay, and once you have this phi, you put this phi into the stress terms. Sigma r then would come out to be 2a2 plus 2a6 theta plus a21 minus a21 minus 2b1 sine 2 theta. That should be somewhere here, I think. There you have it. Okay, this one. But x and y is really not what we want. We want r and theta. So that also I think we had somewhere. We had it written down. Yes, this one. So the phi which you have selected, you have to put in these terms, and then you will be able to write sigma r, sigma theta, and tau r theta. So please verify by putting this phi in this one and see that what we are writing is eventually what you get. Okay, so there you go. So first thing is that you should verify this. Then this is sigma theta is equal to 2a2 plus 2a6 theta plus 2a21 cos 2 theta plus 2b21 sin 2 theta and tau r theta. The shear stress should look like minus a6 minus 2b21 cos 2 theta plus 2a21 sin 2 theta. Okay, and as you can see that all the stress components over here are independent of the radial term. Okay, the general stress field is independent of the radial coordinate. Okay, now we'll be taking some specialized case of this. Okay, one of the specialized cases, well, this if angle alpha and beta are 0 and 90 degree, then it will be a quarter plane problem. So let's write that quarter plane example. What does it look like? The domain looks like this. You have x, you have y, and whatever be your boundary. Okay, this is r, this is theta, and say you have a force shear stress like this, shear traction like this. Okay, so in this case clearly alpha is equal to 0, beta is equal to pi by 2. Okay, and this problem has a uniform shear loading along one boundary, which is the y-axis, and there's no loading on the other boundary, which is the x-axis. Okay, so if you have to write the boundary conditions, so sigma theta r comma 0, again reminding you, don't write the stress directly, write the tractions. From there you will get this. Okay, don't ignore it because it is fatal at a few places if you go wrong. Okay, that's the first one, that sigma theta r comma 0 and r comma, so basically about the x-axis, and then you want to write the same for the y-axis. So sigma theta r comma pi by 2 is equal to 0, but the shear stress on this one will be equal to s. Okay, so again a word of warning, don't write directly. Use the stress traction relations. Okay, so once you put this sigma theta tau r theta of 0 and pi by 2 in these expressions, okay, you will be able to write four boundary conditions, right? Because there are four boundary conditions over here. So those conditions would finally look like 2a2 plus 2a21 is equal to 0 minus a6 plus 2b1 is, sorry, 2. Okay, so these are the 4 boundary conditions which you would have. You can eventually solve them. Let's see, a2, a21, a6, b21. Okay, so it seems there are only 4 unknowns in this question, in these equations. So 4 equations and 4 unknowns. Verify that they give you a2 is equal to s pi by 8, a6 is equal to minus s by 2, a21 is equal to minus s pi by 8, b21 is equal to s by 4. Now once you, so this is again something I'll write for you to verify. If there's any error, do let me know. Now what you have to do is you have to put these a2 and a6 and a21 and b21 back into these equations. Okay, and then we would get a sigma r, sigma theta and tau r theta. So that expression should come out to be this. Okay, that should come out to be sigma r s by 2. Okay, so let's now, first of all, you want to convert this tau r theta to tau xy. See, we can do that. There are transformation relations which we had. Let's see if we can use them. Okay, so let's see. Yes, so should write it in a different color. So if you had this tau r theta, that was minus sigma x sine theta cos theta. I mean, the transformation relation we have already seen. How do we get it? So I'm just writing the final expression. I'm not writing in terms of the transformation matrix. We have done an example about it, how to convert from the Cartesian system to the cylindrical system or so on. Okay, so this is the term. and then plus tau xy cos square theta minus sin square theta minus sigma x sin theta cos theta plus sigma y sin theta cos theta plus tau xy cos square theta minus sin square theta. So we want to eventually find this term tau xy, okay, but for that we will have to slog more, in the sense sigma r has to be written as sigma x cos square theta plus sigma y sin square theta plus 2 tau xy sin theta cos theta, and sigma theta is equal to sigma x sin square theta plus sigma y cos square theta minus 2 tau xy sin theta cos theta. Okay, so sorry, it should be tau xy. So there are three unknowns over here, which is clearly tau xy, okay, sigma x, and sigma y, and tau r theta, sigma r, and sigma theta are the known terms. Okay, so with three equations and three unknowns, you should be eventually be able to write tau xy. Okay, what you want to do now is actually write it. Please solve this and write this, and then observe the fact tau xy is not equal to tau yx at x equal to y equal to 0. So basically at this origin, okay, the shear stresses, the stresses will not be symmetric, and this is somewhat of an inconsistency towards this. Okay, so what you want to, after having observed this, and do not proceed ahead without this, you should be able to write the expression by solving these three terms. It's somewhat easy to do because you already have sigma theta, sigma r, and tau r theta. So this is something which you should write now. Okay, now we want to understand why this inconsistency is happening and what we can do about it. Okay, so let's see, we want to now reformulate this problem in Cartesian coordinates. Okay, so the stress function is equal to s pi x square plus y square by 8 minus x square plus y square by 2 tan inverse y by x minus pi by 8 x square minus y square plus xy by 2. Okay, so this is the stress function which you would be taking. That's again, I mean, if you are not able to guess it directly, that for Cartesian system this is a stress function we should have taken. It comes after experience and putting the boundary conditions and things like that, so you don't have to worry about if you are unable to think how this is coming up. But what you should exactly know is how tau xy can be calculated from this, and that is, as you already know, okay, so this is what you would eventually get. Tau xy is x square plus y square Now if you, other than the origin, so tau xy tends to 0 for y tending to 0, and tau xy tends to minus s for x tending to 0. Okay, you can clearly see that. So if x tends to 0, you would have a minus s, and if y tends to 0, you would have tending to 0. So this clearly has a good limiting behavior, and that is what we wanted, right? If y is tending to 0, okay, if y is tending to 0, you would be coming up towards this origin, so you would get a tau xy as 0 tending to 0, and if the x is tending to 0 coming from this side, you would get tau xy is equal to minus s. So it is telling you the proper limiting behavior other than the origin, obviously. Okay, so proper limiting behavior at r not equal to 0. Okay, as long as both of them are not tending to 0, this is not a problem. So this is one somewhat investigation that you can do, and the crux of the matter is there is some problem exactly at the origin. Okay, and that's why the stress is not coming out to be symmetric over there, and this is somewhat of a proof that other than the origin it seems all okay. Okay, so there are some investigations which go deeper into the subject, but we will be stopping over here. Of course, if you are interested, you can refer to the references given in your text and follow it up later. Okay, now after this, let's take, so we have a quarter plane example, let's take a half plane. So if you look at this diagram, half plane would be formed by two boundaries, alpha is equal to 0 and beta is equal to pi. Okay, so that is how you would form a half plane, by taking alpha equal to 0 and beta is equal to pi. So there are different types of loadings which we will be considering over here. Let's take up the first one, which is half plane under Okay, so first let's define our coordinate system. It's like this. Okay, you should always note that this is how our coordinate system looks like, and then the half plane is something like this. A general point in this is r theta, and then you have a uniform loading, uniform normal stress over x smaller than equal to 0. Okay, so this is that smaller than equal to 0 from this point to over here, and you have a uniform stress over it. Okay, so phi is taken out to be a6r square theta, and this is not coming out from the big expression. All you have to do is just go to this phi, this particular phi. Okay, this, the terms over here can be reduced for this particular problem, and you will be only left out with two terms practically. the A61 and the B21. Okay, this is something which you can easily think why the A21 and the A2 term do not come up over here. Okay, so by the same logics which we have used before, so this should be equal to plus B21 R square sine 2 theta. Okay, think why. Okay, so you must go to the phi of the wedge problem and from there try to reduce this term and see why are we doing this over here. Again, if you use this phi, the Hooke stress sigma theta is equal to 2a6 theta plus 2b21 sine 2 theta, and tau r theta is equal to minus a6 minus 2b21 cos 2 theta. Okay, now you have certain boundary conditions. Obviously, for first of all, this boundary, let me just write it like this, for this red boundary, and let me call this as a purple boundary. Okay, so for the red boundary, the boundary conditions are sigma of theta r comma 0 is equal to tau r theta r comma 0 is equal to 0. Okay, and the purple boundary, that would be tau r theta r comma pi is equal to 0, and the normal stress sigma theta r comma pi is equal to minus t. Again, you should use the stress traction relations. Ti is equal to sigma ij nj. Write the nj in both of them, so it would be like this and like this, and then do this. Okay, so once you do this, you should be able to write the constants. That would be a6 is equal to minus of t by 2 pi, b21 would be equal to t by 4 pi. And once you have found them, you can write the radial and the Hooke stress and the shear stress. So sigma r is equal to minus t by pi sine 2 theta plus 2 theta. Sigma theta is equal to 2 by pi sine 2 theta minus 2 theta. R theta is equal to t by 2 pi 1 minus cos 2 theta. Okay, you can again see that just like the quarter quarter plane problem, the stress field over here will depend only with theta, not with r. Okay, so there is no, it is independent of the radial coordinate. So there is clearly a discontinuity in the boundary loading, and why? Because this particular boundary condition and this particular boundary condition, they are pointing out to two different values at the origin. Okay, one is pointing to minus t, the other is pointing to 0. Okay, so there will be some sort of a problem in the stress as well. So you can see this term over here. So stress terms in general, okay, for theta equal to 0 and theta equal to pi, you will get discontinuous stresses. Substitute it and you will see that directly. Stress at origin. So one of them would give you 0, the other of them would give you 2 pi minus 2 pi, something like that. Okay. So again, you have to convert this tau r theta just like the previous method into tau xy, just to sort of investigate. This is important because you also learn about the limitations of what you are doing, okay? And perhaps this investigation sheds some light of why things are behaving in the way they are. Okay. Now this is the txy equal to minus t by 2 pi 1 minus cos 2 theta. This is something you will verify using again the transformation relation. Okay. Once you have this, so if you have the positive x direction, what would that be? It would be theta equal to 0. So positive x direction. Okay, and then you have the y-axis. Theta would be equal to pi by 2 tau xy minus t by pi. Okay, just make those substitutions and you get these two values. This implies that if you approach the origin along these two different paths, the value will not coincide, and that's not a good thing to be in. Okay, so approaching origin, okay, along the x axis and y axis will give different values of tau xy. One gives 0, the other gives minus in 2 pi minus t by pi. Okay, so there is some problem at the origin, which is somewhat fine, and we'll have to learn to live with it, at least for our limitations. Okay, the theory has some issues which it throws up to us. How we take care of this in our experimental or numerical analysis is something which is entirely up to us. Okay, so there are ways people get around, and we have seen that in the limiting cases, say in the quarter plane problem, it's okay. I mean, the limits approach where it should, like it was approaching minus s and 0. Okay, so in the limiting cases it was working, but not exactly at the origin. So there are ways to overcome problems when you do it in your experiments or simulations, but the theory should be honest, which it is being right in our face. Okay, having done all this, let's move to a slightly more important or famous or involved problem, that's called the half space under a concentrated surface force system. This is also called the Flamant problem. Let's first see how it looks like. we draw the same coordinate system as before. Then you have the loadings are y, x, this is x, this is y. A general point over here is r comma theta. So clearly theta is measured over here. Okay, so I'm removing this just because a lot will happen on this now. Okay, so the objective remains the same, to be able to find the stress field, strain field, and the displacement field within this half space, which is subjected to a concentrated surface force system. Two concentrated forces are there, one is y, the other is x, both shown by a capital sign. Okay. So let's see how the boundary conditions can be applied, but just to note, this is acting at the origin, both of them. I have to show it like this, but it's acting at the origin. So for this, I draw this semicircular arc C, and I write the statement from the text: the tractions on any semicircular arc C enclosing the origin must balance the applied concentrated loading. I'll explain what it is. Now please notice this semicircular arc on C, and I'm drawing that over here. Okay, and then you have this, the origin is somewhere over here, and you have this. Now what is said is that the tractions on any semicircular arc C enclosing the origin must balance the applied concentrated force. So whatever tractions are being applied, okay, I'm just showing it in the most general form, this must balance the concentrated forces x and y, so that this solid, this part of the solid remains in equilibrium. Okay, it's a simple case of force balance. So the tractions must balance, tractions on this surface must balance the concentrated forces x and y. Okay, and so that this part remains in equilibrium, this small part over here. Okay, now the area of this arc semicircular arc is proportional to r, which is this, r is this radius. Okay, so the idea behind this is that the circumference would have been pi r multiplied by a unit thickness inside or outside the plane. Okay, outside the screen at which you are looking at this video. So that is assumed to be y, even if it is not assumed to be 1, whatever it is can be taken, but it will eventually be the proportional to r, because the circumference of the entire circle would be 2 pi r. For us, half of that would be pi r, and this is how you can justify. You need not take this value as 1, you can take it whatever you want, but it will still be proportional to r. Okay, So once the area is proportional to r, you know that the stress is equal to force upon area. Okay, and this would imply that the stress on this arc, okay, must be proportional to 1 by r, because the stress is to force by area, okay, in the most simplistic sense, and the area is proportional to r, and that's why you are able to say that the stress will be proportional to 1 by r. Now what you have to do is out of the general Michell solution, remember the very lengthy expression, choose those terms that will give stresses of order 1 by r. Now since you know that the stresses are of the order of 1 by r, out of those all phi's, take out only those phi's which will give you this term, okay. And again it comes by some experience and some working through the selected terms, hitting and trialing and seeing whether each of those terms eventually give you a phi which is a stress which is dependent on 1 by r. Okay, so that term would be equal to this. It's slightly lengthy, but you should be able to do some small problems of choosing the appropriate r. Okay, now once you have this phi, you can write out the radial hoop and the shear stress. Cos theta plus B12 minus 2A15 sin theta, sigma theta is equal to 1 by r A12 cos theta plus B12 sin theta, and cos theta. Okay, so this will just come out based on this phi which you have. Okay, now let's see. So you want to now apply the boundary conditions. Okay, and what are the normal stresses? Or not just normal, let's call the normal and shear stresses. Okay, coming from the tractions on theta equal to 0 and theta equal to pi. Okay, look at this figure. There is no normal or shear tractions on, hence the stresses on the boundary theta equal to 0 and theta equal to pi. There's only a concentrated force at x, and hence you will say that there is no normal stress or shear stress on theta equal to 0 and theta equal to pi, and this would give you A12 is equal to B12 is equal to 0. Okay, and this would mean that sigma theta and tau r theta would be equal to 0 everywhere. Okay, and for all values of r comma theta, tau sigma theta and tau r theta will be equal to the 0. Okay, so the only stress which sort of survives is this sigma r, which is not equal to 0. Okay, and hence this is also called a radial distribution. Okay, so it can also be shown that if you have a more general case of a wedge domain where the angles are arbitrary, the same result will hold true, meaning this exact result. Okay, of course, I mean, we have found out two constants, a12 and b12, and we still have to find out what a15 and b15 to be eventually write what sigma r is. So that can be done by these considering this fact that the tractions over this semicircular arc C must balance the applied concentrated force. So let's first draw this over here. It's a simple diagram to draw. This is the origin, y, x. So let's balance this forces on the x direction first. So you would have x is equal to minus 0 to pi sigma r a comma theta. A is this radius, okay, of the semicircular arc, and that would be a cos theta d theta, and this would give you minus pi by 15, and similarly y is equal to minus 0 to pi sigma r a theta a sine theta d theta is equal to pi a 15. Okay, so one way to clearly see this is that you have this so-called r sigma r in this direction. Okay, you can call this particular angle is theta, which it is. Okay, at any given r this is there. So sigma r would be this value. Okay, and you have to multiply it by the area, which would be proportional to a. Okay, we had seen that before, that the area is proportional to the radius over here. Okay, and hence you get a sigma r a, and taking a cos theta of it means you are taking this particular direction. So now this force sigma r a over here, if you take an angle theta, you get this force, the component in the x direction, and that is why it is written that x plus this contribution must be equal to 0. Okay, and that's where this term is coming up. Okay, so that's, and similarly for the sine theta as well, the vertical component would be along the y direction would be sine theta. Okay, now once you substitute a15 and b15, so this is not pi, I think it's okay. Substitute a15 and b15 over here. Okay, and then the stresses would come out to be sigma theta is equal to tau r theta equal to 0. So this is what we get as the stress distribution. Now, one of the sort of comments I would want to make, I mean, the stress field which you are getting over here as proportional to 1 by r is not by chance. Okay, remember you had taken specific terms out of phi which would give you stress which would be proportional to 1 by r. Okay, so it's not by chance that it has happened. You have taken terms which led you to this. So this is something which you should keep in mind if ever you are doing an experiment and deviations are possible. I mean, it may not exactly follow this behavior which you have, okay, because you chose it based on our the way we thought about this problem, okay. So this is something which you should keep in mind. It's not like a natural law that it has to be like this. It doesn't really work that way, okay. Now coming back for the Flamant problem or the concentrated surface force system over there at the origin. So as expected, for r tending to 0, sigma r will be tending to infinite. So this is a singularity at origin. Or what is the origin? It is the point where concentrated forces are acting. So this was somewhat expected. It happens. Okay. Now, what we do not anticipate is that sigma theta and tau r theta will be equal to 0 even when y is not equal to 0. See, capital Y, if you remember, is the shear force. Okay, there is a tangential loading. You see what capital Y is over here. Sorry, capital X. Okay. So even though you have a tangential loading in this particular problem, somehow the sigma theta and tau r theta are becoming 0, and this is something which is confusing us. Again, to investigate this, you again convert it back into the xy coordinate system. So let's see how that will be doing. So let us investigate this. I'll put a question mark over here. Okay, so let's put x is equal to 0 just to understand what each one of the concentrated forces are doing, and that would give you, just put x equal to 0 in this, that would give you minus of 2y sine theta by pi r. So this would give you sigma r is equal to minus 2y by pi r sine theta, okay, and obviously sigma theta is equal to tau r theta is equal to 0. Okay, so using this terms, you can easily write out the stresses in the xy or the Cartesian system. So there are transformation relations which we have used and shown before, and this case is actually quite easy because you have two components as exactly 0. Okay, so there is not much to be done by you about this one. So just use the same expressions and you should be able to write that sigma x is equal to sigma r cos square theta is equal to minus 2y x square y by x square plus y square. Sigma y is equal to sigma r sine square theta is equal to minus 2y y cube by x square plus y square and tau xy sigma r sine theta cos theta Fine. So you have found out the stresses in the Cartesian system. Okay. Let's see how this can be seen. Once you plot them on, say, this is the origin somewhere. This is stress. I'll write which stress. So and obviously this is the zero line. So this is tau xy divided by y by a, just to normalize it. And this one is sigma y divided by y by a, again to normalize it. So the distribution of the normal and the shearing stresses on a horizontal line located at distance a below the free surface. So where is this a? This line. So what they're doing is they're plotting sigma y and tau xy on this line, and this distance is a, which is the radius of this semicircular arc. Okay, so that plot is shown over here. Okay, now as you can see that the maximum stress which is directly under the load will be given by sigma y, and that value is 2y by pi a. Just to keep it positive, we are taking the modulus sign. One of the comments which you can make after seeing this graph is that, so if this value is actually minus 5 and this value is around 5 over here, if for x greater than 5a, I mean either minus 5a plus 5a, whatever you can see, the effect of concentrated load is diminished. So whatever fluctuations which you see from 0, from here to here, is happening between this minus 5a to plus 5a, and the fluctuations are happening because of the concentrated forces, which in this case is only y, the vertically applied concentrated force. And after a while, in the sense if you move over here or move over here, it was as if there was no concentrated force. So this is very localized fluctuation in the stresses. Okay, that's an observation which you can make by this particular graph. Okay, now that was for this case. Let's take up y x and the same problem. Okay, y is there and this is your so-called half plane. Okay, so we want to now write sigma r. Sigma r is equal to minus 2y by pi r sine theta. Sigma r is over minus 2y by pi r into sine theta, and obviously you are writing it for r equal to a, which is say a line somewhere below. Okay, so you can write this, you can plot this as this, as this, as this, and so on. Okay, so in all the three cases sigma r is actually constant. Because then sigma r would be equal to minus 2y by pi, sorry, 2y by pi a sine theta. So the lines of constant radial stress are circles tangent to the half space surface at the loading point. Okay, so enough about the stresses. We would now want to find the displacement, and you know how that's done. Once you have found the stresses, you can use the Hooke's law to find the strains, and once you have found the strains, you would use the strain displacement relations to find the displacement. Okay, so to use the Hooke's law, you have to really be clear of what form of Hooke's law to use, plane strain or plane stress. Of course, it's somewhat similar, but there are some constants going up and down over there. Okay, so under the same normal concentrated force only, remember we took capital X equal to 0. We want to assume plane stress, sorry, and the Hooke's law and the strain displacement relations, and then would give you ER is equal to, this is the strain displacement relation for plane stress. Okay, so the strain is like this, and the Hooke's law in this case is sigma r minus mu sigma theta. And this, if you substitute sigma r and sigma theta is anyway 0, so that's not an issue. You would get 2y by pi e r sine theta. Similarly, e theta is 1 by e sigma theta minus nu sigma r. Again, sigma r is pi by theta, and this is equal to 1 by mu tau r theta is equal to 0. Okay, now you have to first integrate this equation, then you would get an answer for ur. Okay, so I am integrating this one and writing it as ur is equal to minus 2y pi e sine theta log of r plus a constant of indefinite integration f theta. Okay, not a constant, but definitely not a function of r. That's the whole point. So f is an arbitrary function of theta. Okay, now you want to substitute this ur over here and over here. Okay, so substitute ur over there, and then you would be able to get u theta. So I'm just doing the first step now, substituting ur over there. Let me show it by a different color. This ur has to go over here, and then this would give you tau u theta
by 2 theta is equal to 2 nu y by pi e sin theta plus 2y by pi e sin theta log r minus f of theta. U theta. Now you would have to integrate this equation just like you did for the last one. So that would give you minus of 2 nu by pi e sin theta plus 2y pi e cos theta. Sorry. Okay. And then you would have a log r, which because the integration is only in terms of theta, and then you would have f theta d theta plus gr, where g is an arbitrary function of r, constant of indefinite integration. Okay, now the question obviously is that do check whether this should actually have a minus sign or not. Sorry, this should be cos theta, so it will definitely, yeah, this will definitely have a minus sign, and then this is cos theta, this will also have a minus sign, so it's okay. Okay, so once you have found out u1 and u theta, clearly we are not satisfied because we have got these two f theta and gr theta, and eventually we have to find these out. How do we do that? We put ur over here and u theta over there, actually, and also over there, because that is equal to 0. Okay, after doing this you should be able to get two relations. Okay, so g of r minus r g dash of r is equal to k, and minus 1 minus nu to y by pi e cos theta plus f dash of theta plus f of theta d theta is equal to k. So k is an arbitrary constant, and eventually you should get gr is equal to cr plus k, and f theta is equal to 1 minus nu by pi e y theta cos theta plus a sin theta plus b cos theta. This is something which I am leaving out for you to verify. Please don't proceed ahead on this video before verifying this. Okay, I have already shown what substitutions you should do. Okay, but you should do this yourself and only then proceed. Okay, once that is done, so you have a b c as your constants of integration, and then you put all of this back into the ur and u theta which we had found before over here, ur and u theta, and we should have ur is equal to, so we are not writing er theta anywhere, sorry, uz anywhere, because it's a plane stress condition. Okay, so there is no uz in this case. Two-dimensional approximation. 1 minus nu pi e y theta cos theta minus 2y by pi e sine theta plus A sine theta plus B cos theta. Similarly, u theta is equal to minus of 1 minus nu pi e sine theta minus 2y by pi e log r cos theta minus 1 minus pi theta sine theta minus 2y by pi e log r cos theta minus 1 plus nu pi e y cos theta plus a cos theta minus b sine theta cr plus k. Okay, so just like we had seen before, you have to recall where we have actually shown this. We have shown before. We did this derivation in all its completeness before. You have to see that proof, okay? That ABC represents rigid body motion. Okay, we have done this in this discussion itself. Okay. This implies that we can set them to any arbitrary value because they will not contribute to the strains and hence the stresses. So we can put them to any arbitrary value because when they eventually differentiate with terms of theta or r, it would not be there. When it would not be contributing to the strains and the stresses because they are rigid body terms. And well, we could do it. And the first thought which always comes to our mind is let's put it to 0. I mean, a few less terms to deal with. But rather than doing that, we would use this to satisfy the symmetry conditions. Okay, let's see what that means. Yes, a lot of them will come out to be 0, but not all of it. So we want to use them to satisfy the expected symmetry condition, as the author in our text says, to satisfy the expected symmetry condition that the horizontal displacements along the y-axis should be 0. Okay, so this is the problem which we have at hand. Okay, yes, this is what y. The symmetry condition is that the horizontal displacements along the y-axis should be 0. So on this red axis, ux must be equal to 0, which is a fair enough argument to make in this loading. So remember, there is no capital X. If there was a capital X, then perhaps we couldn't have made this possible.
Okay, so this we can write as a boundary condition as r comma pi by 2 is equal to 0. Okay, and that would mean that if you substitute theta as pi by 2 in this expression and you have to equate this entire thing to 0, uh, it will require your C is equal to K is equal to 0 and B is equal to minus of 1 minus nu by y by 2e. Okay. Now the capital A is still missing and we have to put it as equal to 0. A will be equal to 0. This is because the vertical rigid body motion may be taken as 0. If you look at this expression over here, okay, at theta is equal to pi by 2, sorry, theta is equal to 0, okay, over here, okay, theta equal to 0 over here, you would have this value as a, and theta equal to pi by 2, this value would be equal to, sorry, theta equal to 0, this value would be equal to a, and theta is equal to pi by 2, this value would be equal to 0. So we want it to be 0 throughout, okay, and hence a has to be put equal to 0 such that the vertical rigid body motion may be taken as 0. Okay. So finally, after putting all this, we would get ur is equal to y by pi e 1 minus nu theta minus pi by 2 cos theta minus 2 log r sin theta 2 theta is equal to y by pi by e 1 minus theta minus pi by 2 sin theta minus 2 log r cos theta minus 1 plus nu by cos theta. So every time there is a log, we start to get worried. Okay. The reason is, I mean, when r tends to 0, log of r starts to tend to infinity, and hence this whole stress seems to be unbounded. Okay. For r tending to 0, sorry, u r and u theta tend to infinity. This is somewhat unpleasant, and that's not a good situation to be in. Okay, so if you take a 3D model for this problem, so this is problem. Okay, if you don't take the plane stress assumption, I'm assuming the plane strain as well, and you take the entire 3D problem, that's called a Bozek's problem. Then this is solved. The reason is that in that solution, the resulting displacements will not have a logarithmic term and it will be bounded in that case. Okay. Again, doing this 3D problem is outside the scope of this particular course, but it's a standard problem available in many elasticity books, so you are feel free to check them out. Okay. Now coming back, we want to also write what UR should be the radial displacements along the free surface. So what is the free surface? Free surface is basically theta equal to 0 and theta equal to pi. So you want to put theta is equal to 0 and theta equal to pi. So free surface. Okay, so you would get the radial displacement as okay. So just put theta equal to 0 and theta equal to pi, and you should be able to get this term, the same displacement. Now we have seen before that for an isotropic linear elastic solid, 1 minus nu is greater than 0. And this is causing a problem. What is the problem of this? The problem is that UR of r comma 0 and UR of r comma pi will be negative at all points on the half space surface. Means this is your okay, this is your origin, and obviously you have a capital Y concentrated force. Now on the surface, both UR will be negative. So this is how the displacements would be on both the surfaces and by an equal amount. Okay, so any point over here will move the same value UR, which is over here, and any point over here will move the same value UR, okay, in this case. This is something which you should verify. Remember that x will be negative at this place, and hence it has to move in this direction, and it is positive on this space, hence it has to move over here to maintain a negative value, a fixed negative value. Okay, so all points on the half surface and they will move an equal amount towards the loading point. The tangential displacement, sorry, r comma 0, same free surface, is given by this. Okay, just substitute theta equal to 0 and theta equal to pi over here, and you should be able to get this. So it will give you this value. Obviously this is singular at origin, because this origin is where the point loading is acting. Okay, and again this is a problem which is solved if you take the 3D case. Okay, again It is outside the scope of this course, but you are free to check up this value. Okay, and to be able to plot the displacement field, in the sense to be able to plot this, where did it go, UR and U theta, okay, you will need a computer. It can't be done with just by looking at these expressions, but I should draw part of it. Say looks, if this is where the y is acting, this is the displacement which I am plotting, and then there are these curves. Eventually the arrows tend to move in this direction, okay, away from this. So a more accurate proof diagram can be checked in this, and you can even plot it if you are enthusiastic about this. But the idea is that it would be somewhat concentrated near this loading, and then it would start to move away. The displacement vectors will start to move away. Okay. So we have seen that there are some problems of this, and of course I have said that in 3D, if you do without stating the proof, these problems would eventually be solved. People have tried to modify somewhat to include these effects in the two-dimensional case as well, but it's not something which we have to worry about now, knowing very well that it is actually an approximation which we are doing, and hence it's okay to okay. Now let's take one more case, actually a very tiny 1.5 more case to be specific, since half is the order of this discussion. So half space under surface concentrated moment. Okay, so this situation looks like this. If you have a plane, and this is how it looks like, X. So you have a P, and then you have a P, and the distance between them is D. Okay, first transform it. So if the concentrated moment is like this, you know that you can replace any force system by an equivalent force system, and M will clearly be equal to PD. Okay, so this, so if you have a concentrated half space under a surface concentrated moment like this, okay, you can just replace this. Okay, and this should give you as sigma r is equal to minus 4m by pi r square sine of theta cos theta. Sigma theta is equal to 0 and tau r theta is equal to, okay. The way you have to do is that you have to first, actually you have already done the first part of it, which is to find the effect on stress on this. Okay, then you have to apply a second problem, which is this one, which is located at a distance d from over here. Okay, and then superimpose the two cases so that you get this final configuration. D must tend to 0, but the final product must, PD must be equal to M, and that is how you should be able to get these terms. So this is something which you have to do. this will be a good exercise to confirm whether whatever we are learning has actually been understood by yourself. Okay. So let's take up the so-called last problem of the day, which is half space under uniform normal loading over Okay, so in this case, the force uh, so this point is A, this is also A, theta 1 angle, theta 2 angle, okay, and this is B. So the loading applies between x is equal to plus A and minus A. So we'll be again using the principle of superposition like we have before. So let's see how this works out. We have already solved a problem for a single normal force. Okay. And we had found out that the stress was in the Cartesian system. The stress was, this was for a single concentrated force. So sigma x was equal to sigma r cos square theta is equal to minus 2y by pi r sine theta cos square theta. Sigma y is equal to sigma r sine square theta. Okay. So if you want to sort of convert this uniform distributed loading into a concentrated force, okay, the way to go about it is write dy is equal to p dx. This is a small p over here since it's a distributed loading. Okay, so we know that for a very small sort of value, let's draw it over here. It's dx So the middle of this, so this is dx, or this angle is clearly d theta. Okay, so this theta is the same as the theta, you know the reasons why, and dx would be equal to r d theta by sine theta. Okay, or in other words, r d theta will be equal to dx into sine theta. This would imply that dy is equal to p r d theta by sine theta. Now, what you do is derive these three expressions, okay, with respect to y, and then we will substitute this dy over there. So that would mean that we write d sigma x is equal to minus of 2p by pi cos square theta d theta d sigma y minus 2p by pi sine square theta d theta and d tau xy minus of 2p by pi sine theta cos theta d theta. Okay. So just to look sort of show this, to verify this, I think you should be able to draw some sort of a triangle in this form. Okay, that's where you would get, so this is r, this is theta, so r d theta would be this one. Okay, and you can take this sine component and that would be equal to dx. Okay, so once you integrate this particular expression, okay, you have to now, I mean, p, remember, was taken as a dy is equal to p dx. Okay, so it was somewhat of a concentrated force simplification, and now you want to integrate it. Where would you integrate it from theta 1 to theta 2. Okay, so from theta 1 to theta 2 you would cover now this entire range, and that should give you sigma x is equal to minus 2 pi by 2p by pi theta theta 1 theta 2 cos square theta d theta is equal to minus p by 2 pi 2 theta 2 minus theta 1 plus sine 2 theta 2 minus sine 2 theta 1. So, okay, so theta 1 and theta 2 have already been defined over here. So just like the previous case, if you want to draw the graph of how sigma y and tau xy vary with x in a problem of uniform loading for a given region, you will again see that the behavior is, again it is at a, so if this was your half plane, this is drawn at a line which is below by distance a. Okay, so this was tau xy by p, this was b sigma y by p, and obviously the origin is over here. This is stress versus x by a. So this is a very similar behavior which we had for a single concentrated force. Remember, single concentrated force graph was also looking okay, it was also looking like this. Okay, sigma y and tau xy were showing a similar idea. And what does this graph tell you? This graph looking similar to the concentrated load. This tells us that the Saint Venant's principle is valid. Okay, now whether you take one concentrated force, okay, or divide this force into small p distributed over an area, the stress field which it would generate at say a given point like this would almost be the same as long as you are away from the boundary or the point of loading. So these two graphs show you and validate this principle. Okay, one can also repeat the same exercise for a uniform shear loading. Okay, and clearly in that case you would take your x as the concentrated force, and in the other case just distribute this as a small s over a region whatever you want. Okay, and we will see a similar sort of validity of Saint Venant's principle over there. Okay, so this is the sort of a summary of our cases of this, and it is what we commonly call as the contact mechanics, which is a subject in itself, but it is somewhat of an introduction. It's again a two-dimensional one, so it didn't have to. So if you have say an indentation, okay, you must have done a hardness testing, and then you put the surface, you have an indentor, and then there is a force which applies, and because of this there will obviously some sort of stress field generated in this region, and if any of them sort of uh, yield, okay, based on the failure criteria, you will all say this, what this method gives you is it gives you the stress sigma ij. You can use your failure criteria to check whether yielding has happened, and if the yielding has happened then there will be some sort of a permanent deformation, and that permanent deformation, which will not go back to zero after the removal of this force, will give you an idea about the hardness of this material. Okay, so this is a very important problem, and we'll follow this up with our so-called fracture mechanics applications that has eventually notch and crack problem, and you will see that we follow it up using the same wedge example which we had considered before. So the wedge problem can be converted to a contact problem and a crack problem, both of them. So we'll continue with this. Thank you. So if you recall the original wedge problem, we had the angle alphas and betas denoted. Let me draw that for you over here. So we had, this was the original wedge problem in which you had the x-axis, y-axis, and this was the wedge. This angle was alpha and this angle was beta. In a situation in which alpha is small and beta is 2 pi minus alpha, you would have something which looks like this, okay, and where this angle is alpha and this angle is beta, okay, and obviously any point on this will be this r comma theta, okay. So when alpha is small and beta is equal to 2 pi minus alpha, the solid looks like this, okay. Now what this does is, this is called a thin notch in an infinite medium. If alpha tends to 0, then this notch becomes a crack, okay. So this is the so-called introduction to fracture mechanics, or whatever you would want to call it. So what you have in front of you is actually a crack. If alpha tends to 0, it is very close to 0. One of the things which we are taking right now is that the crack faces, these are the two faces of the crack, are traction free It will eventually turn out to be stress free as well, but I would want to use the correct definition. And this implies there is only far field loading. Okay. Now the objective is the same. You want to find the stress and displacement perhaps at this point r comma theta in this solid, which has a crack. We have just seen that. So the method goes about similarly. You have to choose a suitable phi, okay, when which r is lambda a sine theta, sine lambda theta, sorry. Again, coming by experience, okay. Do you want the stress fields to follow a certain nature based on the experience, and hence you choose a suitable phi for that. So the only difference here compared to the original Michell solution, the big one, is that n over there was supposed to be an integer. Here lambda is allowed to be a non-integer. We will see why this was necessary in a few minutes, okay, but for now you should note that lambda can be a non-integer. Okay, it can take fractional values. Okay, so if you use this phi and then you write what sigma r, sigma theta and tau r theta would be. So I'm just writing two terms which I'll need now, which is sigma theta is lambda into lambda minus 1 r to the power of lambda minus 2 a sine lambda theta plus b cos lambda theta plus c sine lambda minus 2 theta plus d cos lambda minus 2 theta a lambda cos lambda theta plus minus b. Okay, now yes, there is a sigma r as well, not writing, but this is something which you should verify again. Please don't do the mistake of not deriving these sigma theta and tau r theta and sigma r as well. Okay, you would want to now apply the boundary conditions. The boundary conditions are such that the tractions are 0 on the crack faces. They are indicated in green color over here, and using that you will also find that the stresses are 0 on this crack face. So remember, alpha tends to 0. Okay, so you apply the stress free boundary conditions, actually traction free. Okay, and theta is equal to alpha is approximately equal to 0. That would give you 4 conditions, right? Because sigma theta and tau r theta will actually be 0. So for two crack faces, you will have two conditions each. Okay, so let's first write for theta equal to 0, theta equal to alpha almost equal to 0. This is basically this upper crack face, this one. Okay, so for this, if you substitute theta 0 and alpha 0 in this one, you will get b plus d is equal to 0, and then you will get tau r theta lambda a plus lambda minus 2 c is equal to 0. Now if you come to the lower crack face, which is this one, then you will take theta is equal to beta, which is equal to 2 pi minus alpha. So theta is equal to beta equal to 2 pi minus alpha, which is approximately equal to 2 pi. Okay, that will give you two other boundary conditions. That would be sine of 2 pi lambda minus 2 minus lambda minus 2 pi lambda sine 2 pi lambda c plus cos 2 pi lambda minus 2 lambda minus 2 by lambda sine 2 pi lambda cos 2 pi lambda minus 2 minus cos, oh I'm sorry,
should be minus of cos 2 pi lambda t is equal to 0, and then this would be lambda minus 2 cos 2 pi lambda minus 2 minus of lambda minus 2 cos 2 pi c 2 pi lambda c minus lambda minus 2 sine 2 pi lambda minus 2 minus lambda sine 2 pi lambda t is equal to 0. Okay. Do remember we have also used this in writing this. I mean, other than satisfying this theta equal to beta equal to almost equal to 2 pi and this both stresses being 0, these two properties have also been used over here. Okay. So there are clearly 4 unknowns. A, B, C, D. Okay, and there are 4 equations, linear equations, and for it to have any meaningful non-trivial solution, the determinant of the coefficient matrix must vanish. Okay, so if you write that, the determinant please write these as the 4 linear equations and verify that the determinant would be sine of 2 pi lambda minus 1 is equal to 0. Okay. Now you may be well aware that if the sine of something is equal to 0, it can only mean that 2 pi lambda minus 1 is equal to n pi, where n is an integer. Okay, where n can take a value 0, 1, 2. Okay, I mean negative as well. So lambda would be equal to n by 2 plus 1, where n would be equal to 0, 1, 2. Okay, let me just pose this as a riddle. Can n be negative? Okay, I'll continue to write it as a positive integer, or at least non-negative integers. Okay, now if you look at the stress fields, okay, they are of the order r to the power of lambda minus 2. Okay, and by your own experience you should know that if the stress is of the order r to the power of lambda minus 2, the displacements would be one order up, which is r to the power of lambda minus 1. Okay, just because the displacements are gradients of the, so strains are gradients of the displacements, and strains are linearly proportional to the stresses, and hence, so one order down will be displacements. So near, sorry, I should write it, near crack
tip are tending to 0. Let's see what this means. So if R is over here and R tends to 0, okay, that means you are approaching this point. This point is called the crack tip. Okay. Now we are not going to the crack tip, we are only approaching crack tip. Okay, that's why you have the word near crack tip, not at crack tip. Okay, so the stress or stresses, I mean all the components, will be of order r to the power lambda minus 2, and displacements will be order r minus 1. Okay. Now this is something based on experience. The fracture mechanicians told us, okay, that at this location, which location, are tending to 0, the displacements are finite. Okay, people did experiments and found out that at a point very near to the crack tip, say over here, the displacements are finite. I mean, they may be large, but they are finite. Okay, people did that already, they knew it. Okay, so this is something which we can write. And what would this imply? If the displacements are finite, then clearly lambda has to be greater than 1, because the displacements are of the order of r lambda minus 1. Okay, and if r comes in the denominator, okay, then when r approaches 0, this will become infinitely large, which we don't want. Hence we want that lambda minus 1 must be greater than 0, and that implies that lambda must be greater than 1. Again, people did experiments, and through their own understanding, they knew that at this location r tending to 0, stresses are singular, meaning r has to come in the denominator. That will only happen when lambda minus 2 is smaller than 0 or lambda is smaller than 2. Okay, so if you combine both of these conditions, you will find that lambda has to lie between 1 and 2. Okay, but remember that we have written that lambda is equal to n by 2 plus 1. So let's see, lambda is equal to n by 2 plus 1. So let's see, n equal to 0 would give lambda equal to 1, rejected. N equal to 1 would give lambda equal to 3 by 2. This is accepted clearly. Okay, n equal to 2 would give lambda equal to 2, which is rejected. N equal to minus 1 would give us what, 0.5, right? So remember, we have not actually taken a negative value, But do you see that if we take what happens over here, this, let it be a riddle. What happens, think, how, why, and lots of questions. Because clearly, if you take n is equal to minus 1, you will have this particular value. Okay, so lambda would come out to be half. And I think n equal, okay, sorry, lambda is equal to half is not really acceptable, right? Sorry, lambda is equal to half is not actually acceptable. So n equal to minus 2 would mean that lambda is equal to 0, again not acceptable. So I think you can proudly go back and correct it and say that here n can be negative. Okay, but it doesn't really help you in any way. So the only value which you should take is this. Okay, so this would mean that the stress is of order 1 by root r, and the displacements are of order root r. Okay, now once you take this exact value of lambda is equal to 3 by 2, you should be able to write the expressions of sigma r, sigma theta, and tau r theta. Okay, so you should be able to write that, and I'll just write that expression. Sine 3 by 2 theta minus 3 sine theta by 2 plus b cos 3 by 2 theta minus cos theta by 2 tau r theta is equal to. Okay, so you can see that the stress is always proportional to this 1 by root r, and in fracture mechanics it's very famously called as the square root singularity. Yeah, most fracture mechanicians or anyone whom you know has learned anything about fracture mechanics would always talk about this. You have now seen how this is happening. Why are we getting the so-called square root singularity? We are getting it because we chose the stresses to be of this order. Okay, and we then took out all possibilities and found that only one particular lambda will satisfy. Okay, and that was coming out by the fact that the displacements and stresses were finite and singular at the stress. So we here did not specify what kind of singularity would it be. Okay, we never said it would be a square root or a cube root singularity or just 1 by r sort of a singularity. We just knew that it was singular. Okay, based on it, we didn't know which kind, but it came out that it would be a square root singularity based on what we have done this far. Okay, obviously the major culprit behind all this is always the original phi which you have taken, like in all the other cases as well. So this is no different. Okay, so the objective, that is to be able to find sigma r, sigma theta and sigma r theta in such a solid is satisfied, obviously by satisfying the condition that in the limiting case when r tends to 0, the displacements are finite and the stresses are singular, and that gave us this form. Okay, now it so happens that it's also written in terms of this nu. Okay, so the stress expressions are also written in terms of this angle nu rather than this angle theta. You see theta is something like this. Okay, but the actual applications of fracture mechanics are actually ahead of the crack tip, meaning this region, and somewhat it is convenient to measure new in terms of theta, and it's a more important angle from an application perspective, and hence we don't want to have theta in our expressions. So one can also write these expression just by simply changing. So you can write it as minus 3 by 2. So this is something which you should verify. This is also something you should verify. What's the relationship between, what transformation should you do to be able to get from this to this? Okay, this is something which you should by this time be comfortable doing. So this is not the Poisson's ratio. I just can't make the correct symbol, but perhaps I should say pardon my Greek, but that wouldn't make much sense over here. Okay, sigma theta would come out to be So the solution is still not so-called complete, in the sense you still have this A and B in this, okay? And it seems that you have exhausted the boundary conditions of the crack faces, right? You have taken that these green ticks which you see over here are crack faces and they are traction field. This part you have automatically exhausted. So, but you still have these two unknowns, okay? But we can say that A and B are found from far field boundary conditions, okay? For example, if your solid is like this is the notch, and you have this sort of a loading, so your A and B can be found out using that, okay? This is your X, this is your Y, and so on. So this is how A and B will eventually be found out. One of the other points which you should note, that say with the boundary conditions you will find the value of A and B, but the form of sigma r, sigma theta, tau r theta is independent of far field boundary conditions, okay? So whether you load them like this or you load them like this or whatever else you do, the stress fields will always have this square root singularity. Okay, so the crack tip stress field will not depend on the boundary conditions, the form of it. The value, yes, the number will depend, but if you draw the graph of this sigma r versus r sort of a graph, then that will not change whether the loading is like this black or it is in the green arrows which you are being shown. Okay, now so if you look at the sigma r, or for that matter even sigma theta, okay, the normal stresses, okay, so this is the point, okay, this is the point, excuse me, sigma r and theta, the normal stresses, look at the term A. Actually the coefficients of the term A shouldn't have. This is a function of cos, okay? So with respect to this angle nu which you have found, okay, cos of nu and cos of minus nu would give you the exact same value, okay? Hence it is said that the terms with the A coefficient include symmetric normal stresses, while the remaining terms B have anti-symmetric behavior. Why? Because, well, cos is not a problem, it will always be symmetric, but sine of minus x is the negative of sine of x. Hence B terms have the anti-symmetric components and A has the symmetric components. So let me put that statement with respect is noted. With A coefficient include
symmetric terms, symmetric normal stresses with P coefficient. Have antisymmetric behavior. So it is just so called that these symmetric terms are called the opening or mode 1 behavior, and these are called the mode 2. So it's written in the Roman numerals. There's a mode 3 as well, but we don't have to worry about it right now since we are concerned with only uh, planar conditions. This is called the shear mode. This is called the normal. Okay. So the A and B, which were somewhat related, so K1 and K2 are called the stress intensity factors for mode 1 and mode 2, and there is a relationship which exists. And what are these stress intensity factors? Well, you can just think of them, they are some sort of parameters which tell you whether the crack will grow or not, or whether a growing crack will stop or not, and things like that. So it's more related whether the crack begins to grow. Okay, think of it like some sort of a failure criteria. Okay, and failure in this case is whether the crack begins to grow. So what happens is that if you have a uncontrolled crack growth, is called a fracture. So normally the body will break into two parts by this stage. Okay. Okay. So after this, we can briefly discuss a couple of other examples which you must have learned before in your earlier courses. So think about the pure bending example in which your beam is actually curved. Okay, so think of a curved beam. So curved beams are obviously used in structures and many other applications of it. For example, something like the spring is also made up of curved beams. Okay, so a curved beam looks like this. This is the point R, inner radius is A, outer radius is B, and then there's a bending moment. Okay, so you can imagine how this pure bending is happening. And the definition of pure bending, if you recall, is where you only have the bending moment. There's no other, there's no shear term as such. Okay. So for situations like this, I mean, the objective is again the same. You have to find the sigma r, sigma theta, and tau r theta. Okay. And I'll just briefly go through this. The
answer to this problem, like the answer in the sense sigma r, sigma theta, tau r theta, are all independent of the angle theta. Okay, so it wouldn't really matter. So it's axis symmetric situation. Okay, and then there are boundary conditions. For example, the inner face and the outer face are traction free, so that would automatically mean is 0. Then the tau r theta of A, tau r theta of B is also 0. Okay, the normal stress will follow this boundary condition, and then you can just use the general solution for axis symmetric problem. Okay, put in the boundary conditions. I mean sigma r, sigma theta, tau r theta. You already have a few boundary conditions over here, and then you will be able to get certain conditions that would give you the value of the constants a, b, c in that. And finally you can write, I mean I'm leaving all this as an exercise, please derive this. I have discussed and done this several times, so I think now you should pay me back. You should be able to now do this on your own. Okay, now this is what we get by using this concepts of elasticity which we have learned. But remember, in your undergraduate classes, when you had learned about the bending of pure bending of curved beams, you didn't do all this. I mean, you didn't have to use the Michell's function and then write the boundary conditions and so on. You did it in a way which is commonly called as the so-called strength of material method. Okay, now it does happen that for this problem, in the sense of pure bending of a curved beam problem, if you have the, say, the distance r by a, okay, 1 by 4, and then you have the stress sigma theta a square by m, normalized obviously, and for b by a equal to 4, this is 1. This value is somewhat minus 0.4. It does happen that both of these curves actually are almost, let me use a different color. So this is the strength of material, the earlier theory, and this is the elastic theory. Okay, I have actually not drawn it correctly. The closeness is much better than this. So somewhere something like this. Okay, so for this problem, differences between strength of materials and elasticity theory are very small. Okay, and this is a good time to revise the strength of materials theory. Okay, and then see that how the pure bending of curved beam is found. Okay, please don't proceed ahead without revising this. I mean, you would not be able to compare unless you exactly know what the other theory is. So for any undergraduate course, this should be there, and in most of the books of undergraduate, you should be able to find it. Timoshenko, Crandall, wherever, whatever you want to look at, you will find those values, the stresses. Okay, and similarly, there is this other example of a curved beam under end loading. So this is a situation which looks like this. Okay, so curved beam, inner radius A, outer radius B, at any point r comma theta, the stresses have to be found out. There is one end loading which is shown by this capital P. The stress field depends on the angled coordinate in this case. Okay, so you would have, this is again known by experience, and in this case the experience can come from the strength of materials theory, right? The strength of materials theory, which is a somewhat of a weaker theory, has already told us that what it should depend on. Whether that dependence is correct or not is a different matter, but it has told us already that the stress field depends on theta. Okay, so just like the earlier case, I will leave this out for you. Write the boundary conditions on the surfaces, then do a force balance, then do a moment balance, and eventually choose a suitable phi, which is expected to give the stress field which is dependent on the angle theta. You should finally have sine theta sigma theta is equal to p by n. N is a number which basically depends on the geometry. I'll tell what it is. So n over here is
Actually, not just here. Even in the previous case, n is equal to a square minus b square plus a square plus b square log b by a. And even here, I guess n is equal to b square minus a square minus 4a square b square log b by a. So it's a fixed number. I mean, for a given beam dimensions, n, capital N would be a fixed number. Okay, so this is what one would get for the curve beam under end loading. And if you want to again compare it with the sigma theta a by p r by a, okay, this time the answer would be like this. So this is minus 3. So this is strength of materials, this is elasticity. So again, theta is equal to pi by 2, b by a is equal to 4. So this is at the fixed end clearly. That's why theta is equal to pi by 2. So you can see that for this problem, the difference between strength of material and elasticity theory is more. Okay, so in first of all you should know what the SOM theory is for this problem. Please don't hesitate to look back at your undergraduate book to derive this. You would not get an idea of why you were being taught strength of materials theory before and elasticity theory now if you do not do this. So in general, as you have seen, we cannot say that the strength of material theory is getting very close results to the elasticity theory. But for certain problems like the previous one, the difference is negligible, hence it is okay to consider that theory. In this problem, clearly the difference is more visible, and hence it may not actually be correct to do so. So on the other hand, the strength of materials is somewhat of a much easier theory both to understand and to implement, and hence it is more widely used even with those errors which are there. But since now you are armed with this knowledge of elasticity, you would be expected to give a better judgment of whether or when the strength of materials theory can or cannot be used. And strength of materials theory can only be used in certain simple standard cases. If the problem or the boundary conditions or the loadings are somewhat more generic, then elasticity is the way to go, which you have learned, which you are being taught in this particular course. Okay, so enough about so-called the stresses due to contact and fracture mechanics or the crack problem and so on. So there was some introductions. One last topic which we can take up before we so-called close this topic is called the simple plane contact problem. I had briefly motivated the hardness testing machine or the indentation earlier, but let me now take up a more realistic picture. And this is the so-called contact mechanics. Again, a whole subject like fracture mechanics in itself.
Okay, but we'll just be sort of touching and grazing through this. In fact, this topic we'll be doing it in a much superficial way compared to what we have done even for fracture mechanics. The reason is that it involves the use of integral equations, which at least until this stage is not so-called standard in any courses which you have been taught, including the mathematics courses. So think of this section as just some sort of bunch of formulas which will be thrown at you without proof. But you should be fine considering that just about everything else which we have done in this course has been very detailed and exhaustive and rigorous, and I hope also enjoyable. Okay. So consider that there are gears which are in contact. The tooth of one gear is in contact with the other gear. So obviously they apply forces on each other, and due to that there are stresses generated. And whether the stresses are enough or whether it will cause failure depends on the material and its strength and so on. Similar applications can be found out in tribology and bearings and so on. So, not going into the applications part, there are ways to reduce the contact. Like in fact, in between knee joints, and many of the senior people have this issue that their knees are paining, and the wear is between the lubricant between these in this joint is somewhat disappearing, and because of that there's a wear between two contacting parts. So it's a big field of subject. We are only interested in the so-called contact problem, and how basically the contact between two bodies, in one case, in our case, one is rigid, okay, the other is elastic. How is the contact between a rigid and an elastic body generating stresses in the elastic body? And this is a classic case of an indentation problem for measuring the hardness of any material. Yes, you can also do it for an elastic to an elastic solid, but uh, let's keep that for some other day. So let's take up this case in which, say, we have this. So your origin is nicely kept out like this. This length is A on both sides of the origin. This is a rigid indentor. Okay. And this is UY. Okay, so we're just calling this distance as UY. Okay. We want to now go back to the Flamant problem, okay, in which we had found out that this, so if you recall, where you had a contact, let's see if we can find that. Yes, this one. So we had this situation in which we were applying a concentrated force X in the tangential direction, Y in the normal direction, and we were expected to find the stresses in this case. So sigma r was given as this value, and sigma theta and tau r theta were 0. So let's start with that and say that in the Flamant solution we could write, and we'll see how that can be related to what we are trying to do in this problem.
So for a Flamant problem, sigma r is equal to minus 2 by pi r x cos theta plus y sin theta, and sigma theta and tau r theta is equal to 0. X and y, if you recall, were the tangential and the normal force components which were shown in the figure which we have just seen. Okay, and we had also mentioned that you can find the displacements. We had actually found the displacements for plane stress, normal loading. Remember, we had turned off capital X and then we found out the displacements. Similarly, I had also requested you at that time to turn off Y and let X be, and then find the displacement for tangential loading. This was something which you should have done. If not, now is the time to again go back and do this. Okay, this is what will happen if you don't do it. Will just keep on coming and will continue to haunt us. Okay, this is also one of the questions at the back of your text. Okay, so let me just write out the normal loading, displacements, and the tangential. One plus nu plus 2 log r. I had already apologized for using the symbol nu in fracture mechanics, but that's the only place where I am using that for an angle. Everywhere else, nu is the Poisson's ratio. And for the tangential loading, you have log r plus b. U theta of r comma 0 is equal to u theta r comma pi is equal to minus 1 minus nu by e x plus a. Okay, so a and b are obviously the constants of the rigid body motion terms, and that is something which we knew because we have seen the integration of the strain displacement relations in polar coordinates. So we know that a and b are from the rigid body terms. Okay, so this problem which you have is clearly not a point force, concentrated force, but if you see the rigid indentor, how it's there, okay, it's somewhere like this. So this is a case where the half space is subjected to a so-called distributed loading. Okay, we have seen some cases where we had taken a very sort of uniform P which was distributed, but over here we have the distributed loading. And remember how we had done that? We had done a superimposition. Okay, small element dx was taken, and we had then used the formula for a concentrated load in that, and we found out the answer using the principle of superposition. Okay, in this case also a similar thing has to be done.
Okay, and eventually you should be able to find the stresses and displacements for this. Okay, so let me just now put out how this will look like, because it's somewhat of a lengthy derivation and I had briefly mentioned we will not go to the details of this section, but you should definitely try to do that, because that will only confirm whether you had understood that principle of superposition over there or not. If you didn't understand it there, you wouldn't understand it over here. And how would you do that? See, uy bar is a fixed value. Uy bar is a fixed value. It basically tells you how uy bar is varying with x. Okay, and because this indentor is somewhat of this has taken up a shape which is somewhere like this. Okay, so it's not flat, so called flat. Okay, it involves a lot of Green's function, which again we have not dealt in this course. Okay, so let's call the surface displacements ux bar is equal to 1 minus nu by 2e minus a to x p of s. P is that uniform distributed loading, and s you can understand as the parameter jet that runs in the indentor from minus a to a. And similarly, uy bar would be equal to, okay, I'm sorry for you to be writing this directly, but let's just say that the derivation of these terms is more involved and we don't want to deal with this in this course. Yes, if ever you take up a course in contact mechanics, you would be doing much more than what you are seeing over here. So A1 and A2 again are the terms of the rigid body motion. Okay. Now if you have a frictionless indentor, suddenly the shear terms, which is this T of S, okay, P of X was the normal distribution of, and T of X was the shear distribution. Okay, so if it's a frictionless, clearly T of X will vanish everywhere in the above equations, and we want to differentiate this. Okay, now if you look at this expressions which you have, you can see that there is a singularity at x equal to s over here actually. Okay, and this is the Cauchy principal value you can break down, and this is something which we do normally in, and we are basically stuck with issues like this. Thankfully, it is a singularity of this kind in which you have an x minus s. assumed you had something like x minus s whole squared, x minus s whole squared whole cube, and there are different ways to deal with those sort of things, or x square minus s square. Okay, so what we do is we just take this tiny epsilon and break this integral so that we don't have to deal with that unpleasant situation in which x is actually equal to s. In this case, because of this limit, you would never have x minus epsilon actually equal to 0. It will always be tending to x. Okay. Now, if you take an easier case, okay, an easier case is something like this, a flat indentor. Same issue, a flat indentor. You have this as u y bar. Okay. So if uy is equal to uy bar naught is a constant. Okay. So uy bar naught is the profile of the indentor, and then you will have this as minus a to a p of s x minus s ds is equal to 0. Okay, this is the so-called singular integral equation. Occurs very commonly in contact mechanics. Even the simplest problems in contact mechanics sees this, and that's the reason we are not discussing all this in detail. The solution of this equation is p of x is equal to capital P pi a square minus x square, and P is the total force applied by the rigid indentor. Remember, in any hardness testing experiment which you have done, you would always specify the force. This capital P is that total force which your machine reads, or that's what you are expected to see. How big an indent it has been found, and so on. Depending on the shape of the indentor, you get various values of the hardness. Okay. Now, the contact load distribution, which value p of x, okay, is singular at x is equal to plus minus a. Okay, basically at this point and at this point there is a singularity which we can see. I mean, this will blow off at x equal to plus minus a. And again, this is a frictionless indentor, so called, because the traction, the shear, the tangential distribution had been ignored, t had been ignored. Now you have found out the loading distribution. You can find the surface displacements now. Okay, how would you do that? You have to, this p of x which you have found out, put them over here. Okay, and t you don't have to worry because they are anyway 0. So just put it over here, and then you will get this for this rigid flat indentor. You would get the displacements as ux bar is equal to minus of 1 minus nu. Okay, this is, we are saying bar because it is the displacement of the surface. Okay, it's not the displacement somewhere in the bulk. Now, do recall that the Poisson's ratio is actually between half and what minus 1. Okay, and what happens to 1 minus nu in this range? So 1 minus nu, so if nu is half, this is positive. If nu is minus 1 or greater than minus 1, this is also positive. So this would mean that ux bar is negative. Okay, and just like the previous case, these points will actually move towards the center. Ux is negative, so it would move in this particular direction. So okay, the horizontal surface displacements under the indentor move towards the center. Okay, and you know that if friction was actually present, it would oppose this movement. Okay, because the friction opposes this relative motion, but since friction is not considered, so well, tough luck. Okay, so this is what we have, and after this, again, the details I'm not telling you to derive because I don't expect you would be doing this. But once you have this, actually it is easy, but since we have decided not to get into the derivation of this section, the stress fields in this case would look like this: P of S x minus S whole square or in the integral form minus 2p y by pi square minus a sigma y, just writing out the final term, minus a to a 1 by x minus s whole square plus y square square ds. Okay, and then tau xy would be equal to minus of 2p y square by pi minus a to a x minus s. So what is expected of you is that you would be able to interpret these results. I mean, once this expression has been found out, then you should be able to physically interpret this result. Okay, so if you have to say, for example, find out the stresses tau xy, the shear stresses, and then you have to somehow be able to, because shear stresses, you know that there's a maximum shear stress failure theory. Okay, so that can tell you that if this is the rigid indentor and this is the half plane, okay, and where do you think so this is a maximum shear stress distribution. And these plots cannot be done by hand. I mean, you'll have to use some sort of a program to do this. But to be able to interpret these results, you should know what to do with it. So Px over here is P by a square minus x square and pi. Okay, so this was a flat rigid indentor. You can also have a cylindrical rigid indentor, and that would have its own stress field. Okay, so different geometries, and sometimes it's a V-shaped sort of a indentor and so on. So this is where we end our discussion on the application of elasticity in contact and fracture mechanics, and you see that we have a lot to do with the phi, the original Michell function. Okay, so from that general Michell function, we chose out different values depending on what we wanted to see in our answers, and that what we wanted to see in our answers was coming out of experience. So this is how this entire polar coordinate applications were developed. Okay, thank you.